And all right.
Not yet. Thank you.
5.
I got it.
Oops, hold on. Share. 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 There it is. Share screen. Sure. Yes. Okay.
Yeah.
There we go. Okay, I'll be right back.
I know, I told her. She never responded to my email. She's very selective about that. She did that when I posted it first. But those things like
We are ready. Okay. Can you all hear me out there? I don't know if I.
Yep, loud and clear.
Oh, we can hear you too. Okay, great. Excellent. So before we get started today, did everybody get PowerPoints? They're up here. If you need them. A couple of announcements before we get started with class today. So the first thing is that ARA, I don't know if any of you are going to ARA, but ARA starts tomorrow, I think, and goes through Tuesday. And Jocelyn and I are both going to ARA. So the first thing is there won't be any office hours on Monday of next week, just Tuesday of next week, because Jocelyn's flying back on Monday. So only Tuesday office hours. Second thing is until next Tuesday, if you have any questions, please email me. Don't email Jocelyn because she's going to be at ARA and I want her to be able to enjoy her experience. So send me all those emails. I think that was it, right, for that part. Third thing, I put this on the announcements for the course, but just, if you're trying to set up the maximal reliability, the coefficient H, you want to set that up in M+ rather than computing it by hand, which, by the way, you do not have to do. You can compute it by hand if you want, or you can set it up in M+. It's honestly probably, well, I don't know. 6 of one, half dozen of the other. Depends on how much you like setting stuff up in M+ or not. For the purpose of the assignment, it's probably equally easy either way. If you were going to do this a lot, right, it would be easy to set up the code and just have it there. Anyway, if you want to set up the code in M+ and you want to get those standardized coefficients, for the configurable model, you can just use the variances, the observed variances. But once you get to the tau equivalent and the parallel model, it's a really interesting case, actually, because normally, when we have a model implied variance covariance matrix, like, we might not do a very good job estimating the covariances, but generally speaking, the diagonals are kind of a duh-he. We can always estimate the the model implied variances are usually spot on to the observed variances because, well, I'll save that, but they are. I mean, it's not hard to estimate the variances. But in this case, that's not true because we're making some constraints on this model. We're saying that all in the tau equivalent model, we're saying that all the loadings have to be equal, right? And in the parallel model, we're actually saying that all the loadings and all of the error variances have to be equal. And in those cases, actually, when we generate the model implied variance covariance matrix, it might not actually be the variances themselves because we've made these constraints. They might not actually be the same as the estimated variances. So for the tau, so again, if you want to generate the standardized regression coefficients from the unstandardized regression coefficients for a tau equivalent or a parallel model, you need to get those variances from the model implied variance covariance matrix, not the observed variance covariance matrix. So if you use the observed variance covariance matrix, you'll see that your standardized estimates are a little bit off. They're not spot on. But if you get the model implied variances and you plug those in, you'll see that they're spot on. Yes, Claudia.
I did that, but data, if you use that's only applicable if you use the standardized coefficient, right? If you start from the unstandardized, then you can go, the maximum reliability is going to match the one in the coefficient and the formula. Like if you start from the...
Well, you have to, you lost me because you have to use the standardized coefficients for the maximal reliability.
Yeah, but I use the unstandardized and I convert the unstandardized to the standardized.
Yeah.
And then I just do it like that. If you start from the standardized, that's when the coefficient doesn't match. And that's when I feel like you need to do the implied covariance. The implied.
If you start from, okay, you have two options. You can start from the standardized coefficient.
Yes.
Use the ones that are in the output.
Yes.
That's fine.
Mm-hmm.
Yes. And if you do that, right, it's really easy to just calculate by hand. Just take the standardized coefficients out of the output and just plug it into the formula. Totally fine, right? It's only if you wanted to generate the standardized coefficients from the unstandardized coefficients in M+. Remember how I showed how to do that for the configural model, but I didn't show how to do it for the tau equivalent or the parallel model. And what I'm telling you is, if you want to do it for the tau equivalent or the parallel model, rather than using the observed variances, you need to use the model implied variances. The model implied variances will give you spot on estimates of the standardized coefficients. The observed covariances will be a little bit off. You won't get the identical numbers. So if you decided you wanted to do that in M+ for all three models, just make sure you use the model implied variances for the tau equivalent and the parallel model. Or say, wow, that sounds like a pain in the butt. I'm just gonna do it by hand, and that is also fine. Doesn't matter. Right? Okay. All right. So I think those are all the announcements that I had that I wanted to make. Oh, and I guess the last thing I'll say is, if you're looking for a good resource, there are lots of good resources on reliability. But if you're looking for a particularly good resource, so NCME, which is the National Council for Measurement in Education, they have these things called items modules. Items probably stands for something clever, but I don't remember what, on all different topics. And so they have an items module on scale reliability and structural equation models. So it's Greg Hancock and Gian. And so there's like a primer article, and then they actually have online like M+ code and I think Levon code, all kinds of different stuff. So if the easiest way to actually find this probably is to Google, and I'll put a link to this in our class, but to Google like items modules. I'll make the link because it's not so easy to find because it's not like a regular article. but I'll put the link to the site, and it's really nice because it's not just an article. You'll actually have to create like a free login to get access to all the materials, but you'll find not just an article, but like sample code and sample examples and stuff. So yes.
So I think you said last class to ignore all the like basically part one of homework.
Yes. Oh, that was the other thing. Ignore part one.
So are we going to go over the like Bentler method?
I sure hope so. That my plan is for us to do that today, and you're going to do that part for homework this week. That's the goal.
I was like, I didn't want to.
No, we don't get to it this week. We're doing it next week.
Okay.
But my plan is that we're going to do it this week. So with that said, let's jump into non-recursive models. Yay. This is exciting too, actually. I feel like we've been waiting all semester to talk about non-recursive models. So remember, pretty much all the models we've talked about thus far are recursive models. So they don't have feedback loops. They don't have, we don't have like a disturbance of an endogenous variable, correlated with a causal or an exogenous variable, right? But now this week we're going to talk about non-recursive models. And just FYI, for your homework this week, you're going to estimate a non-recursive model, and then you're going to answer some questions on it. There is one extra credit question, by the way. But yay! What?
I was just laughing because everyone back there was like,
Yay! You'll earn your extra credit on it. No, it's not that bad. It's just there's a little bit of computation involved, but it's not that bad. Anyway, now I lost my train of thought. Oh yeah. So I'm not going to run a non-recursive model today. Like we're going to talk a lot about non-recursive models, but I'm not going to do an example because there's really nothing to show. I mean, there's nothing new about the code or anything. What's new is about like the interpretation, and there's a lot to sort of unpack here, but you'll do an example for homework. We won't do an example in class. Instead, we're going to do, with any luck, we're going to do an example of the nested and equivalence testing, the Bentler stuff. Okay, so moving along. Okay, so there are all kinds of reasons that you might have, error, some sort of correlation between like the disturbance of an outcome variable and your actual like independent variable or covariate, right? So you could have something like, and this sort of sets the stage for some of the reasons that you might have non-recursive models. So, we could have something like this. This is actually probably my favorite example that we'll talk about today. We could have something like a feedback loop, right? And this is cool because today we will learn how to actually run models that have feedback loops. So in a model like this, you've got X, causes, in quotes, right? But X causes Y and Y causes X. But if you think about that, that's like this reciprocal feedback loop, right? So all right. So clearly, and in this particular drawing here, I also have the disturbances, and now each of these have disturbances, right? Because both, if you think about it, both X and Y are endogenous now. Neither of them is exogenous, and that these disturbances are now correlated with each other. Now, that is not actually identified the way it's drawn right now. I'm just showing this like little snippet. I'm going to show you how you could identify this kind of feedback relation in a larger model. But like, if you stop and think about it for a second, you'd be like, well, how could I estimate that? You can't. Like, you cannot estimate A as it stands. Yes?
So I have a conceptual question.
Mm-hmm.
I think I compare work with reading and the brain. And sometimes, like, it's easy to think, like, the brain causes that reading, right? But at the same
The
time,
brain causes what?
like, if you are a co-reader, it's easy to think, like, it's the brain, like, underactivation, right? Reactivation
Okay.
is causal. But at the same time, if you're a co-reader, you're going to read less.
Uh-huh.
Gonna,
So that's
yeah.
exactly what you're talking about, sort of like a feedback loop, right?
Is this a way where you can do that? You can handle that?
Yeah, well, exactly. This is, I mean, again, yes, with limitations, right? I'm not saying like after this class, the sky will open up and the truth will fall out and you will know everything you didn't know before. But yes, this is a way to disentangle those reciprocal causal effects with, like, again, with lots of caveats, right? But yeah, so now we're actually going to be able to model that kind of a and that's exactly right. Like, if you think about interest and motivation, right? We're more interested in or interest and ability. We're more interested in things that we're good at. And then if we're interested in them and then we work harder at them, then we get better at them, right? And then because we're better at them, we get more interested in them, right? And so it's sort of this reciprocal causation kind of thing. So I guess that's why this is kind of my favorite example from what we do today, because I think it is really useful in a lot of scenarios to start thinking about these feedback loops, right? Okay, so that's one reason that you might have a correlation between like the disturbance of an outcome variable and a covariant or whatever. Another is, and I think we've talked about this a bit in class, measurement error in your X variable could also cause error covariant correlation. Or you could have, and this is an important one, you could have some sort of omitted, and this is one of the reasons that keeps us awake at night and keeps us from being able to just say, oh yeah, X causes Y, right? Because there could be some omitted third variable out there, L in this case, that actually is causing both X and Y, right? And so in C, that omitted variable is this variable that it's a latent variable that's not actually in our model. We haven't measured it, but it exists and it causes X and Y. And when we go to estimate the XY path, right, we're going to overestimate the effect of X on Y, because sort of mushed in there is going to be the effect of L on X, that shared variance of the effect of L on X and the effect of L on Y. So there could be, and we're going to talk a lot more about omitted variables too. There could be some sort of an autoregressive error structure, right? And then I'm not even going to talk about spatial effects, but there could be some sort of spatial effects. That is not my shtick. All right, so okay, so a structural equation model is non-recursive if any of the outcomes in the model, so any of the endogenous variables in the model, directly affect one another in a reciprocal relationship, or if there's some sort of a feedback loop at some point in the system of equations. So basically, the causal path can be traced from a variable back to itself, right? So if you start somewhere and you sort of end up back there, if you can end up back there, or at least some of the disturbances are correlated with each other. But as I've mentioned earlier, if you only have correlated disturbances in a block recursive pattern, so, and I'll show you some pictures of that in a little while, those are a lot easier to deal with. So technically, anytime you have correlated disturbances, you have a non-recursive model. But if you have a block recursive model, if you have correlated disturbances that are block recursive, that's not necessarily that hard to deal with. Okay. All right. So again, we talked about stationarity when we were talking about autoregressive models. So we make the assumption of stationarity here, and really stability too. I mean, we're sort of thinking that especially when you think about these reciprocal models, these reciprocal causation models, or really any of these models, we're really assuming that we have sort of reached a point of equilibrium in our model, right? That things have kind of things have kind of leveled out, if you will, right? So we have sort of constant coefficients over time. If you're you could imagine there are all kinds of dynamic systems, right? And if you're sort of in the middle of a vastly changing system, then, this is not, we're assuming that that's not the case, right? And in some sense, that makes sense, because if you're in the middle of a vastly changing system, whatever you estimate right this minute, those aren't going to be the right parameter estimates, in a couple days or in a couple months, right? So we're sort of assuming that, even though we have these feedback loops, that the system has reached some sort of an equilibrium, which really means that, there is some longitudinal consistency of some of the aspects of the model over time. and more technically that the joint probability distribution of the variables doesn't actually change when you shift it in time. So you go a little bit this way or a little bit that way. I'd still expect to see the same joint probability distribution. I'd still expect to see the same sort of, pattern of variances and covariances. So again, sort of bottom line, that the path coefficients are stable. They're not changing across the course of the feedback cycles. There is feedback, right? But that we can actually get some sort of a decent estimate of that. Okay, so that's just something to keep in mind. Again, another, important assumption. So this is what I was saying. So we've reached equilibrium, right? So we haven't sort of entered this system too early. And, we also are going to make the assumption that sort of a virtually unlimited sequence of feedback cycles makes sense for the phenomenon. So when we talk about these feedback loops, we're going to just sort of assume that they're, sort of almost like an infinite series of feedback loops. Now, obviously, there's no statistical way with a cross-sectional design to verify whether the assumptions of equilibrium or stationarity are actually tenable. So again, you can actually estimate, so like statistically, right, modeling wise, you can take a cross-sectional model and you can estimate reciprocal feedback loops. But the right, you should take that a little bit with a grain of salt, right? Because you don't, with a cross-sectional design, you have no way of actually seeing whether you've reached equilibrium, et cetera, right? So like a pure cross-sectional design. So we assume, again, we assume equilibrium and stationarity, but, and violations obviously can be problematic, but, depending on the way your data are collected, you may or may not be able to test those assumptions. Kaplan et al. In 2001, he actually simulated like a dynamic system. So it's like a, again, it's sort of a system with these, feedback loops. So there was some perturbation, so it's a dynamic system and it's headed toward equilibrium, but it hasn't gotten there yet. So sort of imagine this system that's in flux, but it's sort of heading toward equilibrium. And then he looked at cross-sectional studies sort of conducted at different numbers of cycles before equilibrium was reached. And, he found that, not surprisingly, the estimates of the effects that you get varied widely depending on sort of which cross-sectional sort of, snapshot you took on the way to equilibrium. And you might imagine, this also makes sense that the differences were greatest for systems that were like oscillating dynamic systems where so in an oscillating system, you can sort of imagine that the effects were sort of swinging from positive to negative, right? And again, it's sort of a duh-he, but obviously, like if you have this crazy oscillating dynamic system, it hasn't reached equilibrium yet, and you just take a snapshot at one point in time, that's not going to be the same as the snapshot you would get at another point in time, right? But it's kind of a nice paper where he kind of shows all that. And Wong and Law, looked at a cross-slide panel model with reciprocal effects, and they found that you do better with cross-sectional samples when there's greater temporal stability, so you've got stationarity and equilibrium. When the non-recursive model, so if you've got a feedback, and we're going to talk a lot about this today, if you've got a feedback, loop, reciprocal causation, that you actually include a covariance between the disturbances of those two variables. When you have a larger sample size, so, he found like 500 is way better than 200. That's always bad news for us, right? And then that the relative magnitudes of the external variables were sort of approximately equal instead of really, really different. Okay, so now I want to talk, to sort of get us started, I want to talk about two different kinds of models with indirect effects, two completely different approaches, two completely different sets of assumptions about what's going on behind the scenes. And those two approaches are first, and we've talked about this already, mediation, right? So this is sort of what I would call like a standard sort of SEM or regression approach to dealing with mediation. I should have had a little picture, but you remember, right? We've got X, we've got the mediator, we've got the Y variable. I've got a picture in a minute. And then the other is what's called an instrumental variables approach, which is sort of a way of dealing with endogeneity, which I'm going to explain what instrumental variables are, and sort of we're going to compare and contrast sort of a mediation model to an instrumental variables model. So in an instrumental variables approach, we've got some sort of a problematic causal variable. We've got like a variable, an X variable that affects a Y variable, an endogenous variable, but there's also a correlation between the X variable and the disturbance of the Y variable. And you might be saying to yourself, wait, no, that's not possible. We learned in regression class that you are not allowed to have a correlation between your independent variable, your covariate, and the disturbance of your outcome variable, right? Like that. So what you're saying is wrong. Like it cannot be done. Well, yeah, okay. That is an assumption of OLS regression, is that there is no correlation between the disturbance of Y and the covariate. But that's actually turns out to be, just because we assume, it's just like everything else. I feel like, when you really get into statistics, you learn that, not half, but a large portion of stats is all about assumptions, right? If I make this set of assumptions, I can do this. If I make this other set of assumptions, I can do that. And in some sense, at a certain point, you end up battling assumptions with assumptions, right? Like which set of assumptions, and sometimes you can't check those assumptions. Like again, in quant 1 or whatever, we can check the assumption of normally distributed data, right? That's easy. But like some of these other assumptions are not actually even empirically testable in the same kind of way. So you sort of have to decide which assumptions am I comfortable with. So you're going to see we're going to have a battle of assumptions here. But anyway, so if you're thinking to yourself that's not possible, well, it is possible. It's just not possible in OLS regression. Okay, so let's talk about this. So we've got this nice mediation model. So we've got X is our predictor, right? M is our mediator, and Y is an outcome variable. And what assumptions do we make with a standard mediation model? Well, the first really important assumption is we're assuming that there aren't any unmeasured confounding variables that would explain the relationship between the mediator and Y. And that's true for X and Y too, but I'm going to kind of zoom in on the MY relationship here just because it'll make a nice contrast to the IB approach in a second. So we're really assuming that there is no sort of omitted variable I haven't measured that's going to account for that relationship between M and Y. Again, or X and Y, but and we're also assuming there's no measurement error, which we've talked about before. And obviously, if either of those things are problematic, we can't make any sort of causal interpretation. All right. But assuming there are no unmeasured confounders, then I can actually estimate what's the direct effect of X on Y, what's the indirect effects of X on Y through M, right? What's the direct effect of M on Y? Great. I can get the total effect, blah, blah, blah. Okay, so now here's my IB model. So now I've got X is predicting Y, but there is some sort of unmeasured confounder out there. So X isn't the only thing that predicts Y. There's some other thing out there that predicts both X and Y, okay? And so for that reason, you can see I've put a correlation between the disturbances of X and Y. And that's really saying the piece of X that isn't explained by, the IB in this case, and we haven't talked about that yet, but, whatever, the disturbance of X is correlated with the piece of Y that can't be explained by X. And in fact, well, okay. So there is some sort of correlation between X, right, and the disturbance of Y. That's the really important thing. Now, the good thing about a model like this is it allows for the existence of unmeasured confounders. So it allows for endogeneity. And it doesn't assume, okay, so that's good. So we don't assume that there's no relationship between X and the disturbance of Y. And we don't have to assume that there are no confounders out there. But we're going to trade that assumption for another assumption. And here's the assumption that we're going to have to make. We're going to find an instrumental variable in order to be able to actually estimate this model. So if IV weren't there, if that green box were not there, this model would not be estimable. It would be unidentified. So to identify and estimate this model, allowing for the correlation between those disturbances there, what I'm going to have to do is find an instrumental variable. That's the IV there, so not independent variable, but instrumental variable in this case. And this IV needs to be related to the X variable. And it needs to have no direct effect on the Y variable after controlling for the X variable. So it should be related to Y, but only through X. So the only way that the instrumental variable is going to be related to Y is through X. There's not, so this is really super important. There can't be a direct effect of the instrumental variable on Y. There can't be any kind of relationship between the instrumental variable and Y that isn't completely explained by the X variable. You with me? And I mean, and this is the tricky thing. And because I need to make that assumption for this model to be identified, I can't test it empirically, right? Which means I have to be able to make a theoretical case that the only way that this instrumental variable is having an effect on Y is through the independent variable. Or, I mean, if you have multiple independent variables, it could be through multiple independent variables, but that there's no direct effect of the instrumental variable on Y. And again, not empirically testable. And this is the hardest thing. Actually, instrumental variable techniques are super cool, but the hardest thing about them is finding a good instrumental variable. And I think that's the place where, lots of criticisms get lobbed at sort of research. I've seen countless articles where, I'm like, I don't really buy that. I don't buy that as an instrument. I don't know that I buy that the only way that this variable would be related to this variable is just through this other variable. So I have a couple of examples I'll show you. It can be tricky to find good instrumental variables. Okay, so again, the true underlying model here is, okay, there's W here is some variable that we're not really measuring. This is a confounder. It's predicting both X and Y, right? And so if you think about it, if there is a confounding variable predicting both X and Y, one of the ways that we can sort of account for that in the model is by allowing these disturbances to, even though I don't have this variable, so I can't model it directly. If I allow these disturbances to correlate, then I can sort of account for the fact that X and Y are related to each other because of some unmeasured confounder, right? So if I just try to measure this path of X on Y, or X predicting Y, and the confounder isn't in the model, what happens to our path coefficient? Well, I mean, obviously it ends up being biased because, and it ends up, let's assume that this confounding variable positively predicts both X and Y. Okay, it's the easiest thing to think about, but it's going to be biased no matter what direction it is. But let's just pretend it's positive for now. So if W positively predicts X and if W positively predicts Y, but I don't have W in the model, then what's going to happen? That x, y, I'm going to attribute that shared variance between x and y to the effect of x on y. But that's going to be a mistake, right? Because really there's some other third unmeasured variable out there that's actually predicting both x and y. So when I estimate my beta coefficient, it's going to be positively biased. It's going to be too big, right? Okay, so because I don't have a W, I should allow the disturbance of y to correlate with x, right? That would solve this problem, but obviously in this two variable system, I can't do that. I'm under-identified. And again, I said, remember in OLS, we're always assuming that this doesn't exist, right? Like OLS always makes the assumption that this is 0. But not assuming that this is 0 would sort of solve that problem. So I'm going to go out and I'm going to find an instrumental variable z, and I'm going to assume that z predicts x and x predicts y, right? And that there's no direct, and that z, I mean, there's going to be no direct effect of z on y after parceling out the effects of x. So whatever relationship z and y have, it's completely mediated by x. This is like an IV model is like a complete mediation model. But again, you can't test for complete mediation. You have to assume it. Okay? So the instrumental variable has to correlate with x, and it has to be uncorrelated with the disturbance of y. Not uncorrelated with y itself, but uncorrelated with the piece of y that isn't explained by x. So that's really what that no direct effect of z on y after parceling out the effects of x means. Okay, so let's say, I'm going to use a little covariance algebra here. So let's say, let's think about the instrumental variable solution for B. So in a regression, right, y is just equal to the intercept plus beta 1 times x. So that's just like the slope of, right, x, and the disturbance of y. So that's just a regular formula for the regression, for a regression equation. And okay, so what's the covariance between y and z? So that's the outcome variable, the y variable, and the instrumental variable. So we can say, okay, that's going to be the covariance between, what I've done here is I've just substituted the formula for y. See, let's see, right? I just said this is the regression equation for y. So instead of saying covariance of yz, I just plug this in for y. So I've substituted this whole thing in for y. So now I'm saying the covariance of y and z is just the covariance of, right, beta naught plus beta 1 times x plus the disturbance of y and z. Now, remember I said we're going to assume that the covariance of the disturbance of y and z is equal to 0. So if I can assume that covariance of that disturbance of y, the disturbance of y and z is 0, then what I get is that the covariance of y and z is just beta 1, this falls out because it's a constant, so you have beta 1 times the covariance of x and z. And then I can compute the regression equation, the regression coefficient, beta 1, by just, right, simple, I'm going to divide by the covariance of x and z on this side, right? Divide by the covariance of x and z on this side. And then what I get is that the regression coefficient B1 is just the covariance of y and z divided by the covariance of x and z. And now contrast that to the OLS solution for the regression coefficient. The OLS solution for the regression coefficient is the covariance of, x and y, right, divided by the variance of x. So here, instead of the variance of x, we have the covariance of x and z. Which again, if you think about it, in OLS, there is no covariance between x and z, right? So really, that's why in OLS we end up with the variance of x, basically the covariance of x and x, which is the variance of x, because we make that assumption. So without making that assumption, we end up with this as our regression coefficient. So that's what I'm saying here. So when x equals z, if an explanatory variable can serve as its own instrument, then the covariance, if the covariance of x with the disturbance of y is 0, then the instrumental variable estimator just reduces to the OLS estimator. So basically, ordinary least squares is just a special case of IV when we can assume exogeneity of the x variable. And remember, exogeneity means, right, there's no path from, or no correlation between the disturbance and the independent variable. So we take this, and if we can use x as an instrument for itself, then we get the standard OLS regression formula that the regression coefficient is just the covariance, right, divided by the variance of x. Great.
You here's the disturbance of y?
What?
You and that slide?
Yeah, you in the slide is the disturbance of y. That's right. Okay, so let's take an example to make this a little bit more concrete. So here's our true underlying model, let's say. So there's this. So again, there is no direct effect of z on y after controlling for x, but z predicts x, and that path coefficient is 0.5, x predicts y, that path coefficient is 0.5. So what would be the model? Let's assume these are standardized path coefficients, just for simplicity. So what would be the model predicted correlation between z and y? Yeah, I mean, if you just it's like just thinking across the top there, right? It would be 0.25, right? So again, it's not that we're saying that, and I just want to sort of emphasize that, because it's not that we're saying that z is not correlated with y. In fact, that would be a lousy instrument. It's that after controlling for x, z is not correlated with y, that z doesn't predict y, okay? So now there's also this confounder out there, and let's say the confounder also predicts x and y, and those coefficients are 0.5 each, right? So obviously, okay, well, so what happens? So if I fit an instrumental variables model, it would look like this, right? I allow for this disturbance covariance, the covariance between these two disturbances, and I'm going to get z predicts x, x predicts y. I'm going to get 0.5 and 0.5. And then the correlation between the disturbances is going to be 0.25, which makes total sense, right? Because remember, we had a 0.5 path and a 0.5 path. And so if you kind of do the tracing rule there, you would expect the correlation between x and y to be 0.25, right? And that's what you would get. And you would actually get sort of the right answer here. Okay, what happens if I mistakenly fit a standard mediation model? Bad things happen when I fit a standard mediation model, okay? So now here, remember, like we're trading one assumption for another. Over here, just a sec, and it is sort of the battle of the assumptions. So I can't tell you what's the right model because it really depends on your research and your data, right? You've got to do the heavy thinking here. But right here, I am assuming there's no direct effect of, right? There's no direct effect of z on y after controlling for x. So that's a big assumption. But I'm not assuming that there aren't confounders that explain both x and y, right? And I'm accounting for that, and I'm getting the right answer here. In this next slide, I'm obviously not assuming that there's no direct effect from z to y because I'm estimating that path, right? But what I'm assuming is that these two disturbances are uncorrelated, right? So I didn't make that assumption. So in the last slide, I allowed these two disturbances to correlate. I assumed that this path was 0. Now I'm allowing for a direct path from Z to I, but I'm assuming that these disturbances are uncorrelated with each other. And now look what happens, right? If the last model was right, you can see, okay, well, Z to X, I still get a 0.5 path. That makes sense. I mean, if you kind of think about what's going on, nothing's going to change there. But I get a huge overestimate, actually, of the XY path, which makes sense because it's absorbing that, confounding the variance, that shared variance that's a result of that confounder. And then I'm actually getting something that looks like a little bit of like a mild suppression kind of effect here, right? So I'm actually getting a slightly negative direct effect of Z on Y after controlling for X, which is, a little bit weird, but that's how it works out. So I would fit this model and I would say, oh, wow, look, I have, and remember, the solution to this problem isn't just to drop out that ZY path. Like you might be thinking, well, just like that -17 is weird and that might not be statistically significant. So why don't I just drop, and it might not be actually, why don't I just drop out that path? But dropping out that path doesn't solve my problem because remember, my problem is that the disturbances are correlated. So even if I don't estimate, even if I were to assume a complete mediation model here, because I'm not allowing the disturbances to correlate with each other, I'm going to way overestimate that XY path. Now, I don't have another example that says like, well, what if the mediation model is correct and you estimate the instrumental variables model? I could. I mean, but bad things will also happen. That's why I'm saying it's really important that you theoretically figure out what's the right model, because these are assumptions you need to make, but they're not necessarily empirically testable. I thought I saw a hand. Yeah.
So in this case, our non-indices with point that we should be for.
No,
Not necessarily.
no, because this is just identified. I only have 3 variables, right?
So I can't.
Yeah. So in terms of model fit,
If I were to drop out that path.
yeah, if I were to drop out that path, then I'd be over-identified, right? But yeah, so yeah. But I mean, really, you can't like this problem is not solved by modification indices. You really have to do the thinking up front. Yeah.
So just to clarify, there's no way to tell if this model or the instrumental variable model that allows the disturbances to correlate is better except your theoretical knowledge.
Yeah, I mean, really, I mean, it does pretty much mostly come down to theory. So that's the question. Like, which is more?
Because I would look at this and know that 0.83 is.
No, that's exactly right. You could run this model and you'd be like, hey, here's my mediation model.
Okay.
And you don't realize there's a confounder lurking out there that's really driving that 0.83. And so you present this and you're like, ta-da, and you're wrong. So, and that's exactly what we're talking about it, because that's problematic, right? And happens all the time. And this is one of the reasons that people sort of bang the gong of mediation is not causation, right? Like, just because you can run a mediational model doesn't make it a causal model, because there could be an omitted, I mean, for lots of reasons, but probably one of the biggest reasons is because there could be this lurking omitted variable out there, right? And so you think X causes Y, but really there's something else out there that causes both X and Y.
So if you're having like journal reviewers or something, you can't necessarily rely on like numbers necessarily to back it up. You just have to be like, look, based on this other literature, I think this is this other thing that we didn't get to measure.
Yeah, I mean, so one of the biggest, and I know this is tricky, but one of the best things you can do if you want to fit these mediational models and you want to be able to stand on firm ground, I mean, obviously, we talked a little bit about not measuring everything cross-sectionally is good, but that's not enough. The other thing is measure any variables you think are possible confounders, right? And put them in your model. If you know there's a big old confounder out there, you should be measuring it and putting it in your model. And so if you have the big, that's the thing. If you have what are the theoretically important confounders that you know from prior literature, then you're in much better stead to be able to say, right? So like, you should have had W. You should measure W. W should be in your model. If W is in your model, you're fine. If W is not in your model, I mean, you can do these things like sensitivity analyses to say, how big would an omitted confounder have to be to really substantively change the nature of my results? Like how big a confounder that I didn't measure would actually appreciably change my results. That's sensitivity analysis, and that's always a good idea. Because the reality is that like we're never going to have every single confounder, right? But we should have the big ones in there. And so if you have the big ones in there and you can show that like, oh yeah, there might be a few little other things out there, but I think I got the big ones. And if there were just a little bit of confounding, wouldn't really change my results very much, then you're in good shape, right? Yeah. But yes, that's true. I mean, like lots of people don't ever think about this. They get data, they fit mediational models, they get paths, and those paths may be just wrong because they may have this problem that there's some omitted confounder out there that really explains that relationship, and they should really be allowing for a disturbance covariance, but they're not fitting an instrumental variable model. And maybe one of the reasons they're not is because they don't know about it, or maybe they're not fitting an IV model because they can't find a good instrument. Because honestly, that, in my opinion, is the hardest thing about instrumental variables, is finding a good one, right? Because that's an equally tricky assumption if you think about it. Like it solves this problem, yay! But then you have to be able to make the case that whatever this independent variable is, it only predicts Y through X. Or, I mean, again, you could have multiple X's, but there's no direct effect of my instrumental variable on Y after controlling for the other variables in my model, which really means that the disturbance of Y can't be correlated with the instrument, which, by the way, if you stop and think about it, that sounds an awful lot like the OLS. We like just pushed our OLS assumption sort of down the path a little bit, right? Because with the regular OLS regression, I was like, hey, there's no correlation between X and the disturbance of Y. And now I'm like, oh no, there could be a correlation between X and the disturbance of Y. I just need another variable out there that doesn't have a correlation with the disturbance of Y, but does predict X and does indirectly predict Y through X. So you, like, in a way, I mean, it's really cool, but in a way, you've also just kind of kicked the can down the yard a little bit, right? And if you can't find a good instrument, oh, then you're in trouble. Yeah? All right. Do you find this class depressing? I feel like I'm always bursting people's bubbles. Like, yeah, don't do that. Yeah, don't do that either. I don't mean to be that way, but I'm just telling you where all the landmines are hidden. All right. So, okay. So I think I said all of this already. But I just will point out that an instrument, I've been showing this instrument as an exogenous variable, but like we can have these big SEM models. An instrument could actually be an endogenous variable in your model. It just has to have these characteristics that I was talking about. But other things could be predicting an instrument, I think most of the examples I show, it looks exogenous just for simplicity. So again, the most important thing is it can't have a direct relationship with the outcome variable or any omitted variables that influence the outcome variable, right? And when we have a feedback loop, we're going to need one instrumental variable for each endogenous variable in the feedback loop. We'll talk about there's like a little technicality there that actually we'll be able to get away with one fewer IB if we don't allow for the disturbances to be correlated. But we'll talk about that in a sec. And obviously, if you can pull it off, it's better to have more than one instrumental variable, because if you can find a couple IBs, then you have like an over-identified IB model, and then like you know, you sort of have more options, right? Maybe if one of them ends up not being good, then you still have another one to fall back on. Yeah.
Do you mean more than one IV in the entire model, or more than one IV for each endogenous variable?
Well, you're going to need one IV for each endogenous variable that you have problems with.
Okay.
I meant more than one IV for each problematic endogenous variable, ideally, if you can. Okay. All right. So we're going to need as many instrumental variables as there are variables needing an instrument. The instrumental variable has to predict the variable that needs an instrument. And if you have a feedback loop, the same variable cannot serve as an instrument for both variables in that loop. But here's the exception. If you have a feedback loop, one of the variables doesn't need an instrument if you don't correlate the disturbances in that feedback loop. And again, you have to be able to make a theoretical a priori argument that this is a good instrument, because you can't actually test this assumption. Okay, so here are a couple of examples of instrumental variables. So let's look at the first, and these come from, oh, I should have brought that little green book. So there's this really nice, if you want to read more about non-recursive models, there's, I think I put this on the syllabus too. There's this really nice green, I call them fastbacks. Sage, I don't know what they're really called, but Sage has these, or little green books. Have you seen these? They used to be really popular when I was in a grad school. They're these like little books that are bigger than a chapter, but smaller than a book. You know, they're about this thick, right? Like about 100 pages or a little less on different topics. Sage sells them. They're like, I don't know, probably 200 in the series now. And this is one of those books. So I don't know, it used to be like $12. It's probably like $18 now or something, but they're less than $20 for these little books, which is kind of nice. And this one is, not all of them are great, by the way, but this one is great. I highly recommend this one. So both of these examples actually come from the Paxton little green book, because it's hard to think of good examples of instrumental variables, you know, that people won't. And I think a lot of times people be like, well, what about this as an instrument? And I'll be like, I don't really buy it, you know, but I buy these. So we'll see what you think. Again, you don't have to, but they're at least they're a good sort of to start poking holes at. Okay, here's the first model. So what we've got is we've got a husband and a wife, okay? And we're looking at their political party affiliation, sort of their political attitudes or whatever, right? Are they sort of liberal, conservative, whatever? And we think, hold on, the husband and wife are over here. We actually think that, like, okay, you're married. It kind of makes sense that, like, there's going to be some sort of a reciprocal feedback loop, right? Between, you know, between husband and wife's political affiliations or whatever. So right, that makes sense. So we've put in, so we're saying, yeah, okay, what wife's political affiliation or political persuasion is affecting husbands is affecting wives. And then what do you think that we've got a correlation between the disturbances? That means, what does that mean? Let's see if anybody can tell me what it means. Yeah. Yeah, that accounts for unmeasured confounders. Like maybe there are things that, you know, something that happens externally to both of them that affects both of their political persuasions, right? Yeah. Or, you know, strong, yes, right? Or, you know, something that happens to change their mind, right? Something happens. Or they've got a kid, or they both work at whatever. Well, if they both work in the same industry, I mean, to a certain extent, yeah, that could be. So anyway, so other external things that would be potentially these confounding variables that would be influencing both the husband and the wife. And that's why we like to have in feedback loops, we sort of prefer to be able to allow the disturbances to correlate. It's a like, and again, if you have the two instrumental variables, you can allow the disturbances to correlate. Then you can test whether you need that correlated disturbance. It's really nice if you don't need the correlated disturbance. that actually kind of makes for a stronger model because, you know, now you don't have some unmeasured confounders sort of predicting both simultaneously. It really is the feedback loop that's explaining the nature of the covariance there. But if you don't have an instrument for both the wife and the husband, so if you don't have an instrument for each of these endogenous variables, then what happens is you could actually estimate this model without this disturbance correlation with just one instrumental variable, but you'll be under-identified if you want to put this in. So it's better to be able to put this in and have an instrumental variable for both problematic endogenous variables. So anyway, okay. So here are our instruments. See if you buy it. So the instrumental variable for the wife's political persuasion is the wife's parents' political persuasion. And the idea here is that wife's parents are going to influence the way she sees the world, and she might influence the way her husband sees the world. But again, the theory here is the wife's parents are not going to have a direct effect on the husband's political persuasion. It's going to be indirect through the wife. Okay, I buy that. You know, that makes sense. And on the flip side, you got the husband's parents' political persuasion predicting the husband's political leanings. And the husband then, of course, you know, has an influence on the wife. But the same thing is true here. We're saying there's no direct effect of the husband's parents on the wife other than through the husband. I don't know. You buy it? And then obviously, what? No? And notice, we are also allowing the husband and wife's parents' political persuasions to correlate, which makes sense too, right? Like the husband, you know, so, you know, again, think about it, like somebody who's conservative is likely to have conservative parents, marry somebody conservative, that person's likely to have conservative parents, right? So it kind of makes sense that there's probably some correlation between the parents' political leanings. They're exogenous variables here. So okay, maybe you buy it, maybe you don't, but it's better than some examples, let me tell you. Okay, so that's example one. No, this we can fit.
With the correlation between the two.
Yeah. This we can fit.
Well, then I missed your earlier point.
No. My point was, if we can fit this, if we want to fit a reciprocal causation with correlated disturbance like this, so we actually got this, and this, we have to have an instrumental variable for each of our problematic endogenous variables. If we didn't want to have this thing, well, here, right here, let's just contrast with, both of these are identified. If we don't want to put a correlation between the disturbances, we just want to have a feedback loop, then we can get away with just one instrumental variable instead of two. But again, the problem there is that then we really have to be able to assume, I mean, it's like we got another assumption that we're loading on here now. We have to be able to assume that there is no correlation between the unexplained parts of these two problematic endogenous variables, that there's no sort of confounder that might explain these two things, right? You know, the parts. So anyway, so it's better, if you can pull, it's better to be able to do this. But this is identified, and this is identified. But this is a stronger model. But these are both identified models. Okay, so let's talk about the second. Oh, yeah.
So for that first model, there is no direct effect of the wife's parents' political views on the
There's no, that's right. And it's theoretical. We're not testing it. We can't test it, right? But what we're saying is there's no direct effect of the wife's parents' politics on the husband's politics. And there's no direct effect of the husband's politics on the wife's politics. That doesn't mean there's no relationship, right? Because there is a relationship. Yeah, I mean, if you think about it, there's a relationship because you've got this affects this, and also these are correlated, right? So there are sort of two pathways by which the husband's parents' political persuasions are actually correlated with the wife's political persuasions, but there's just no direct effect. Yeah? Did I see another hand somewhere? No? Okay. So our second example here is, okay, so this is kind of interesting. So this is they're political scientists, by the way. You can get that from these examples. So the idea here is you've got congressmen, and the instrumental variable is how the person voted, and the X variable is actually how their constituents perceive they voted, which is kind of an interesting idea. So how they vote doesn't really matter. What matters is how people think they voted. And obviously how people think they vote is going to be should be predicted by how they actually vote, right? But it's not actually the same thing. And the idea is their actual vote is not going to have any direct effect on their approval except through what people's perceptions of their vote are. That kind of makes sense, right? Kind of clever. And here you can see we only have one instrument. So we can fit this feedback loop, but we actually can't allow for a correlated disturbance. Yeah? All right. All right. So what do I want to say here? Okay, so in this example, here we've got x1 is the instrumental variable, which again, it's directly affecting y1, but not y2. And in this case, the way I've drawn it, because there is no correlation between the disturbances, so this is identified the way it's drawn here. The instrumental variable makes this model just identified, and that allows us to actually get unique solutions for the C path and the D path. So the C and D path are the two paths in that feedback loop. And if you think about it, the instrument is appearing in the equation for y1, but not in the equation for y2, right? Because there is no direct effect of the instrument on y2. Okay, so why is this instrumental variable so important? Well, the feedback loop, if you think about it, between y1 and y2, it really is giving us like three contrasting hypotheses about the causal process that underlies this observed association. Could be that y2 causes y1, or y1 causes y2 causes y1, or some of each, right? And in an experiment, we would manipulate one of those variables, and then we'd look for effects on the other one. But of course, we don't have an experimental design here. But an instrumental variable is sort of like a like a natural experiment, if you will, sort of a quasi manipulation. Because we're assuming that x1 does not directly affect y2, and this is why that assumption is so important, then any association between x1 and y2 is evidence in support of the y1 to y2 path. So the idea is, okay, I'm assuming there's no direct effect. So whatever relationship there is between x1 and y2, it's got to be traveling through y1, right? And so that's actually helping me to identify that path, right? And then, and then sort of once we sort of have that, then we can also, then that allows us to sort of, get this other path. So, for example, if we had this is just sort of dovetailing on what I was saying before. Now I don't have a D path. If this were a model without this path, this model says there is no relationship between x and y2, right? Because if you look at it, think about the tracing rule. There's no way to get from x1 to y2 in this model, right? So the only way that this model is going to, if this model fit, it would be saying there's no relationship between x1 and y2. And so the relationship between y1 and y2 is going to be completely just a function of the relationship between y1 and y2, right? And yeah.
Are we going to talk about how we get data showing no association between them?
Well, I mean, this is more theoretical. I'm not saying you're going to have no association. I'm just sort of saying, like, I'm making the point that this is why having this instrument is really helpful, right? Because, right, it's helping you to identify that D path.
So I'm struggling to figure out how we implement that. Like, you just make a model that.
Yeah, you just do, yeah, like, in terms of modeling this, you just have to make sure that your model is identified. So you need to have an instrument for each problematic endogenous variable. Yes.
Without a feedback loop that I can see, I wouldn't have thought that this was non-recursive. Can you explain why?
No, this isn't non-recursive. The whole point of this was just saying, no, the whole point of this was just saying, like, if there were no path here, right, then, like, what I'm saying is that anything that's here, right, this path is helping us to really identify this y1 to y2, right? So what we're doing is we're saying, like, I know that x1 does not directly affect y2, right? And so, like, any effect of x1 on y2, it has to be pushed through that D path, right? And that's why the assumption is so important. I can't test it, but it's so important because I'm really saying, like, to the extent that there is, right, like, to the extent that x1 is affecting y2, it has to be happening through that D path.
So with the D path omitted, that's why I'm having a hard time understanding it.
Well, I'm just saying, if there were no D path, that would say if there's no D path, that's saying there is absolutely, in this model, it's not non-recursive, but this model is saying x1 and y2 are completely uncorrelated with each other. The model that we fit is this. So if I look at the correlation matrix, I'm going to see a correlation between x1 and y2. But I'm making the assumption that that correlation between x1 and y2 is mediated by y1, right? Which is why I can't check the assumption, because it's not like I'm saying there's no correlation between x1 and y2. In fact, again, that would make for a lousy instrumental variable. What I'm saying is that there is no direct effect. And so I can kind of use, so then what I'm doing is I'm using this to help me figure out this pathway, right? Okay, let's keep going. Maybe, so the instrumental variable helps us to figure out how much of the association of y1 with y2 is due to the influence in this one direction. And then what happens is we, like, assign the residual association to the influence in the other direction. Right? Like, any of the shared variance between x1 and y1 and y2, it can't be in this pathway. Right? The shared variance between these three variables has to be in this path. See what I'm saying? But there might be shared variance between these variables that they don't have in common with x, right? So if there's residual association between y2 and y1, right? After controlling for that, then that's like the other direction. So we're using the instrument to help us understand, to sort of help us. Well, you think about it, and again, it's not a perfect system, but we have to have something, because how else are we going to get two paths, right? For, like, the same relationship between two variables. So we're really saying, like, okay, in this one direction, there's, like, this shared variant, right? X predicts Y, right? And then, the piece of Y that isn't explained by X, is the disturbance there, right? And then we've got Y1 predicting Y2, Y2 predicting Y1. And we're using this to actually help us to identify these two paths. Okay. So again, makes it a really strong assumption of no common causes of y1 and y2, because if there is, then that association could be a result of those common causes, right? And that's why we'd like to be able to correlate the residuals, which again means that we would have to have another instrumental variable here. All right, so again, So we're thinking, we've got, three sort of issues we need to think through with instrumental variable estimation. We've got, this issue of spuriousness, right? That an unmeasured variable might be causing both the endogenous and exogenous variable. We've also potentially got these reverse causation issues, right? The endogenous variable might be causing the exogenous variable. And of course, measurement error can rear its ugly head. And even if we have measurement error, that can actually cause us to have endogeneity problems. Yes. So these are, okay. So, all right. So let's take a look at this for a sec. All right. So look at this model. What are the problematic causal variables here? Like, what are the variables that would need instruments? Y and Z, that's right. Do we have instruments for each of those variables? Yeah, Q for Y and X for Z, right? And since we have an instrument for each one, are we identified? Are we over-identified? Under-identified? Don't even think about counting like all of the paths. Just think about in terms of identified for this reciprocal part of the model.
Without U and V, doesn't that make it not actually have one more than you need?
Yeah, exactly. So this is like, I would say this is like actually over-identified in terms of thinking through that, the instrumental variable part of the model, the reciprocal causation. We could, in fact, actually add that covariance between the two disturbances and still be identified. So that's why I say the model's over-identified, right? Because both of the problematic causal variables have IVs and the disturbances aren't correlated. So now, the way I've drawn it with the correlation, I would say, from an IV perspective, this is just identified. Like I can model it, it's just identified in terms of being able to model the problematic causal variables. Okay. All right. Which is exactly what I just said here. So that's what I did in this slide. Okay. Let's take another look at another picture. Okay, so here we've got, this is what I mean, by the way. Well, actually, if we didn't have these, this would be block recursive, right? Block recursive means you've got a recursive model, but you just have like disturbances that are correlated. This is actually truly non-recursive now because we've got the feedback loops. But it is still block recursive in the sense that, all the this is a block, this is a block, this is a block. And you can see across blocks, the model is recursive, but within blocks, it's non-recursive. So that's what block recursive means. All right. So here we've got, Y2 is a problematic causal variable, Y1 is a problematic causal variable, right? Do we have instruments for both of them? Yeah, we do, right? And so we can correlate the disturbances just like we did. And then what about Z? What about Z1 and Z2?
Did you say that Y1 and Y2 are instruments for Z1 and Z2?
Yeah, that's exactly where I was going. Y1 and Y2, though they were problematic themselves, right? And so we needed instruments for them. They can serve as instruments for Z1 and Z2. Again, you have to be able to make the assumption there's no direct path from Y1 to Z2, no direct path from Y2 to Z1, right? But yeah, absolutely. So here we actually have 4 problematic variables and we have 4 instruments. So we're okay.
Do you
Yeah.
have an example of, in reality, a construct where you would have that many?
Oh. It's so hard to come up with good instrument examples, but let's see. Like I could be sort of I'll cop out and say, okay, let's go back to our parents, the parents and the spouses, and maybe that doesn't work. It can't be their kids because they share the parents. Yeah, maybe, right? If they don't share, I mean, it's tricky, right? something. I mean, off the top of my head, I don't know. Let me give me some time to think about it. But I mean, there definitely are examples of things like this. I'm not thinking of a really great example off the top of my head. Thinking of good examples of instrumental variables in general, ones that you totally buy, I think are not, not always so easy, but I'll come back to thinking about a good example. Okay, so now we need to talk about total effects and model implied correlations in non-recursive models. So notice that, and again, first, notice that the picture on the side here is a non-identified. I've just zoomed in on this piece of the model, okay? And I'm saying the structural equation for each of the y variables, each of the problematic causal variables includes the other one, right? So y1 is cy2 plus d1, and y2 is dy1 plus d2, right? So there's sort of, if you think about it, you know how we could often we'll substitute. You could substitute in for all of the equations and get to your exogenous variables if you wanted to. You can't do that here, right? Because if you substitute cy2 plus d1 in, but again, there's like this feedback loop, right? So we've got this kind of feedback going on because we've got the equation for the one variable includes the other. So that's really the sort of the essence of feedback. So, just so really sort of familiar example of positive feedback is, when you're on a Zoom call, right, and you sign in from two different devices or whatever, and you get this like, right, you get some sort of audio feedback. The microphone, like you've got two mics going in the same room, and the mic is picking up sound from its own loudspeakers. It amplifies it and it sends it through the speakers again, and that's why you get that horrendous sound, right? And then you can see here, so this is a picture. This is a picture with like mirrors, right? It's sort of like this infinite loop, and this Land O'Lakes box is here. Boy, they've changed that box, and rightfully so, because it is definitely not. It's a lot of cultural appropriation there, but the reason I put it on there is I remember when I was a little kid, back in the 70s when people were not very, thoughtful. I remember staring at this box and just being like, wow, she's holding this butter box, and then she's on the butter box, holding a butter box, and then she's on the butter, right? And then like, where does it stop? Like, how far does it go? And so, while I appreciate that they should totally have changed the butter box, I was like a little bit sad because it was my first thought, it was my first foray into feedback loops. So I keep it here to remind myself of that. Anyway, but if you think about that, then when we're thinking about like model implied correlations and direct effects not so much, but total effects especially, like, right, when we're thinking about total effects of like y1 on y2, and again this is not identified the way it's drawn right now, but just to kind of think about this, what we really have are what are called loop enhanced effects of each variable on the other variable, because remember, if you want to know what the effect of y1 on y2, it's d, but that we're not done, right? Plus c times d plus c times d, right? That's the nature of the feedback loop, is that you've got sort of this infinite series going on. So the effect of y1 on y2 is d, but then you can loop back from c to d, right? And then, plus, so you've got this sort of d plus d times c times d plus d times c times d times 4, right? And so on and so forth. Now, the reality is that, as you sort of go on in this series, these numbers get increasingly small, right? And so there's actually, even though the loop goes on sort of infinitely, the effects do at some point become vanishingly small. And so actually there's a nice there's a nice formula. Oh, I'm not sure the formula yet, but okay. So again, if y increases by 1 unit, the first loop adds 1 times d, right? Times c, and so on and so on, right? So you got 1 plus 1 times d times c plus 1 times d times c times d times c, and so on and so forth. So imagine if c and d are 0.5, then the total effect of y1 on y2 is actually d plus d times c times d times, and it goes on and on and on. And it would actually give you, if you did this out until the numbers get small enough that you don't care anymore, you get 0.6666666. If c and d are 0.5, then actually, even though, the d path is 0.5, the loop enhanced effect of y1 on y2 is 0.66666. Now, it turns out there's a really nice formula, an easy formula, so that you don't have to do that. And it is to just take the effect and divide it by 1 minus CD in the denominator. So the loop enhanced effect of y1 on y2 here, we had d is 0.5, right? And c times d is 0.5 times 0.5, which is 0.25. 1 minus 0.25 is 0.75, right? And so we can take 0.5 divided by 1 minus 0.25. Oh, I already said it's 0.75. 0.5 divided by 0.75 is 0.6666666. So when we want to compute what the total effects are here, we can't just, right? We need to use these formulas to get these loop enhanced effects. So here the total effect of y1 on y2 is 0.66666, even though the path is 0.5. Well, both paths are 0.5 in this case. And obviously what both paths are is going to affect what this loop enhanced effect is, because in the denominator it's 1 minus CD, right? All right, so here it is. So this is it. So the multiplier is really just going to be 1 divided by 1 minus those two paths. Okay, so get out of here. There we go. So if we want to think about so we already talked about the loop enhanced effect of y1 on y2. The loop enhanced effect of y2 on y1 is just going to be c divided by 1 minus cd. What about, now this is interesting too, we got to think about the effect of a variable on itself, right? So the loop enhanced effect of y2 on y2 is just going to be, again, let's sort of assume we're starting at a 1. 1 divided by 1 minus CD. And the loop enhanced effect of y1 on y1 is 1 divided by 1 minus CD. So we can compute those loop enhanced effects. And that is kind of interesting too, again, because, it really is that this variable y1 is actually being influenced, right? This reciprocal feedback loop means y1 is also increasing across time. Yeah.
So if a variable has an effect on itself, how do you go about interpreting?
Well, I mean, so again, let's assume that these CD paths are positive, right? So you're getting something like 1 minus CD was what, 0.75. So now you're getting 1 divided by 0.75, which was 1.333333, right? So what it's really telling you is that y is getting, I mean, again, there is even with cross-sectional data, there is sort of this assumption that, right, this thing is kind of happening across time, right? So the idea is that, let's say this is, let's say it's self-concept and achievement, right? So as self-concept increases, achievement is increasing, and as achievement is increasing, self-concept is increasing. And what that means though then is, again, if these things are positively related, your self-concept, is being influenced by, your self-concept isn't just static. It isn't just one. It's being influenced by your achievement, which is then influencing your self-concept, which is then influencing your achievement, which is then influencing your self-concept, which is then influencing your achievement. So that's why we need these multipliers, these loop enhanced effects, because it's not like the idea is that as your self-concept goes up, your achievement is going up, which is making your self-concept go up by even more. So there's this, right? So that's kind of how you interpret it. So there is sort of this magnification of the effect. So you're not statically going to be in the same place because, right, as your self-concept goes up, your achievement's going up, and as your achievement's going up, your self-concept's going up. So it's sort of showing that these things are, right? It's that kind of idea, this looping. Now notice, this is important too. How do we compute the correlation between Y1 and Y2? This is not a typo. It is not a typo. It's C plus D. So we take the two paths divided by 1 plus C times D. Okay, and I know that looks weird at first, and you're probably like, no, that's wrong. No, it's not wrong. It is C plus D divided by 1 plus C times D. So again, if our correlation, like imagine our paths were 0.5, so we have, 0.5 plus 0.5 is 1. So like right there, that should tell you, okay, well, that's definitely not a typo. It shouldn't be minus. It needs to be plus, right? Divided by 1 plus 0.25. So the model implied correlation between Y1 and Y2, if both of those paths are 0.5, is actually 0.8. Thank you. All right. And we can do the same thing here actually for like the, even if we're talking about X1, which is now this instrument, right? What's the loop enhanced effect of X1 on Y1? Well, it's actually going to be A divided by 1 minus CD. And the loop enhanced effect of X1 on Y2 is going to be A D divided by 1 minus CD. And that's like the effect of this IV. Okay. So what's the effect of X1 on Y2, let's say? So again, the effect of X1 on Y2 is 0.3, but because Y2 has an indirect effect on itself, it's really going to be, it's going to be 0.3, but then again, we've got this looping, right? And so we can do that. We can compute that by taking A times D divided by 1 minus CD. So here we actually get, 0.6 times 0.5. Let's see, CD is 0.2 times 0.5, so we divide that by 0.9, and we get a 0.33333. And you'll see that feedback effects, because these are decimals, right? They do tend to dampen out pretty quickly under, after a relatively small number of cycles. So when CD is positive, so that means if both paths are positive or if both paths were negative, when the CD is positive, the feedback loop amplifies the effect of X1 on the other variables. And obviously, if the CD product is negative, it dampens the effect. Probably more common to see positives, but they can be negative too. So here you go. If it's negative, right, the effect of the feedback loop is actually to counteract or diminish the effect of the X on the other variables. So that's like a negative. It's like a negative feedback loop. It's easier to think of positive examples, but sometimes there are negative. Yeah.
Are all these calculations done with the standardized coefficients? Yeah. I think
yes. All right. You could have two instruments, right? So we could have a feedback loop with two instruments. There's nothing really too much to say there, except for, again, if I want to think about the loop enhanced effect of X2 on Y1, now I've got, again, so it's like I'm doing this indirect effect, right? The BC path, that's normally how I would get from X2 to Y1. But now I'm dividing it by this multiplier. So it's BC divided by 1 minus CD, right? And And again, the model implied correlation between like y1 and y2, just as an example, again, it's just going to be c plus d divided by 1 plus cd. So we're just going to use this. I mean, it's really not hard to do these computations. We already talked about the advantages of a second instrumental variable, which, okay, well, just to, right, we can, it's helpful in terms of getting proper solutions too. We didn't talk about that. And it's also, as I said, it sort of strengthens the logic of the model, and just remind you that if we can estimate that covariance between the disturbances and it's not statistically significant, that's great. Then we can get rid of it from the model, and then that actually, we can make a case that there aren't these other spurious causal effects out there, right? That really X and Y1 and Y2 are actually responsible for their joint relationship rather than other variables outside the model. So that's really nice. Okay. This is just an example. You could kind of figure out what's the model implied correlation between y1 and y2. Oh, and I do that. So what's the model implied correlation between y1 and y2? Okay, and well, think about all the ways you can get from y1 to y2 here, right? Well, we've got c plus d divided by 1 plus c plus d. So that's that first piece that we talked about. But I could also get from y1 to y2 by going, all right, the first way is here. The second way is here. So now I've got a times, I said a times b times g, but a times g times b, right? That's probably an illogical order, but it's the same thing. So a times g times b, again, divided by that multiplier, 1 plus cd. And then also we got the correlation here between the disturbances. That's h, right? And again, I am assuming that we're using standardized coefficients for all of this, because we're talking about model implied correlations, right? So h divided by 1 plus c plus d. So I can just take all of that together, and that will actually give me the model implied correlation between y1 and y2.
Are those three terms generalizable to any two instrument model such as this? I'm just thinking that one homework where it was like, list that all, and it became like, do you know what I'm saying?
Well, I mean, the bigger the model, the more.
But I'm saying like with a model such as this where there's like 2 problematic variables, 2 IVs, like it's just pretty much the 3 terms that you'd be thinking of.
Well, yeah, I mean, again, but in a model of this size, right, if I started putting some others,
Right.
because this is the model implied correlation between y1 and y2. So the question here is, remember what we asked with model implied correlations. It's like, what are all, right, we have to account for all the different ways that that y1 and y2 could be correlated with each other. So what we're doing here is really saying, okay, just like for a minute, forget about the non-recursive aspect for a sec and just say like, okay, how could I get from y1 to y2, right? Just like we did in week 2 of the semester. The first way would be this, a times g times b, right? But now I'm saying, but I can divide that by 1 plus cd, right? What's the second way I can get from y1 to y2, right?
Backwards forward.
Yeah, well, it's going to be this h path. These should be ones there. Because, okay, so anyway, the h path, and so that's going to be h divided by 1 plus cd. And then the last way is, right, I've got that, and what, like again, this is this reciprocal feedback loop, and I said the way we're going to estimate that correlation is c plus d divided by 1 plus cd. So really all I'm doing is I'm saying, I'm harkening back to like the second week of class and thinking about model implied correlations, but then I'm using these rules to actually come up with what they would be. So it's generalizable in that sense, but that's why I sort of hesitate to say, because like if I put another variable, right, I could have something else going on in here too, and then there might be other things that need to be accounted for. Yeah.
Is ENF part 1? Do you have to do
E and F are always gonna be there. They're always gonna be one. Yeah, I must have stolen this picture from somewhere else. There are two different ways that you can actually estimate disturbances. The standard way is to constrain the paths to be one and to estimate the variances. And that's in the year 2022, pretty much what everybody does. But way back in the olden days, like in the 70s, people used to use a different way, fairly commonly. I mean, there were sort of two different ways. And the other way was to estimate the paths and constrain the disturbances to be one. You can't estimate both. You can either have the variances or the paths. And definitely, like constraining the paths to be one and estimating the variances, that's the default for every software package. It makes a heck of a lot more sense. Like, why do I want to constrain the, I mean, like, I don't know. Like, it just doesn't, and frankly, if you do this, you can, they're mathematically equivalent, so you can like get back to what the variances are, but like, nobody really does that anymore. It's called the path analytic formulation, or the path analytic sort of specification. I used to teach it in class, but I stopped because like nobody uses it anymore. So I was like, who cares? Anyway, so those are always going to be one. So you really don't have to worry about it. Okay, here we go. So I think I said all of this. Oh, yeah, this is a cool model, I think. Okay, here we've got an indirect feedback loop. So we've got, like, this is 3 variables, and it's actually like a full, it's like a circle, right? It is, we don't actually have like a feedback loop between any 2 variables. We have like 3 variables in a triangle. So y1 predicts y2, y2 predicts y3, y3 predicts y1, right? So like, the better I feel about school, the more motivated I am. The more motivated I am, the better I do. The better I do, the better I feel about school. The better I feel about school, the more motivated I am. The more motivated I am, the better I do, right? You know, or right, or something like that. Maybe I should say more motivated. Maybe I should say the more work I do. Motivation without actually doing something is probably not that useful. But anyway, you know what I mean. So that's that kind of, so now we've got like a 3 variable system. I'm better at thinking examples for this than the crazy block recursive instrumental variables one I'm still thinking. But that's cool, right? So this is a cool model too, because even though we don't actually have any exogenous instruments, it turns out that this non-recursive model is just identified. So you can fit this model. And you know, I've listed out the structural equations. And okay, what's the model implied correlation between y1 and y2? You might not be too surprised. The model, okay, think back to our rules about how do we get the model implied correlation. The first way that we can get from y1 to y2, oh, and I apologize, I noticed that there are a bunch of y2s here, and these are graphics. So I try to like put stuff over them, but that should be y3 there, sorry. So y1 to y2, the first way is through the A path, right? Again, forget about the fact that this is non-recursive for a second and just think about the model way we can get model implied correlations. And then the second way would be going, right? We could go y2 to y3, y3 to y1, remember? So that would be B times C, right? But again, we have these multipliers here. So what we could do is, in this case, it's going to be A plus B times C divided by 1 plus, and now here it's A times B times C, because we've got 3 variables that are in this system. So again, the numerator is just like the model implied correlations that we did in the beginning of the semester. And then, but then we really have to adjust for the fact that we have these feedback loops. Okay, so here we go. So total, if we want to look at the total effects, you know, of these indirect feedback loops, again, we have like the total effect of y1 on y2, and the total effect of y1 on y3. Okay. And, you know, just to kind of, just one thing to be careful about is, you know, when we use this kind of a model, which is really cool, be careful because the flow of effects has to all be in one, you know, like, again, it's not, you know, we've got the flow of effects sort of all in one direction, and this unidimensional causal flow assumption, it has to be plausible, like, you know, it has to be believable, because again, it can't necessarily be tested empirically unless you have, you know, more variables in your model. So you have to be able to make a compelling case that this is good and right. Okay, so I think I already said that. Oh, because I went backward. Okay, so so again, this feedback loop, if you think about it, this 3-path feedback loop is really then amplifying the relationship between the variables to an increasing extent as the path coefficients become larger. So let's assume like if A, B, and C were all 0.1, right? Then we could figure like the model implied, you know, correlation there is like, you know, 0.11, right? So that, you know, between A and B or between, sorry, Y1 and Y2 or whatever, between two of the variables, because they all have the same correlation, they all have the same path now. So like from 0.1 to 0.11, that's not a big change, right? There's not a lot of sort of magnification here. But if all of the paths are 0.33, then the model implied correlation between any of the two variables is 0.38. So you can see it's sort of getting bigger, right? And if the paths are all 0.5, the model implied correlation between any of the two variables is 0.67. And finally, if the paths are all 0.7, the model implied correlation between any of the two variables is 0.89. So you can see that like the amplification is smaller as the paths are smaller, right? And that amplification gets bigger as the paths get bigger. Okay. So again, just a couple cautionary things to think about. You know, our feedback loops have to be theoretically driven. They have to be conceptually sound. And, you know, we have to really think through what are good instruments. And an exogenous variable is not a good instrument just because you erase a path. Like that does not make something a good instrument, right? And then the identification rules are way more complicated for non-recursive models. We're going to talk about some of those in a minute. You know, if we have a just identified recursive model, it's always going to be identified. It's going to be just identified. It has 0 degrees of freedom or whatever. But you can have just identified non-recursive models, you know, or models with either 0 degrees of freedom or even positive degrees of freedom that are actually non-identified, that are under-identified. So, you know, we've sort of started to talk about that with the instrumental variable sort of conversation, and then there's also this empirical identification issue, like, well, how much does the instrumental variable need to be correlated with the problematic causal variable, right? Like how much does this, you know, how big does this correlation have to be, right? So you can kind of imagine that, you know, again, it doesn't have to, you're not expecting a perfect correlation by any stretch, but the correlation can dip so low that it can become problematic. Like, you know, yeah, it's okay, there's some correlation, but it's really, 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 really small. And so, you know, that can actually lead to empirical under-identification, which leads to then improper solutions. All right, let us say this one thing and then we'll take a break. So, and then we'll come back and talk about identification rules. So for R squared in non-recursive models, I mean, think about it, right? If you think about like what's going on with those non-recursive models for a second, the disturbances and the causes are correlated. That sort of violates the assumption of OLS regression that allowed us to neatly partition the variance into the variances, right? The sort of explained and unexplained variance. So the variance doesn't simply partition into the sums of the variances of the latent predictor plus the disturbance term the way that we get in OLS regression. So there have been actually a variety of different methods that people have come up with to kind of get some sort of a, like an estimate of an R squared or an R squared like thing for non-recursive models. Bentler and Raycob came up with something called the Bentler-Raycob corrected R squared, which is reported in EQS. There are a variety of other R squared measures. In some sense, R squared becomes a little less useful too, because we just like these models don't function the same way, right? But there are a variety of ways to sort of think about sort of quasi R squared measures, but we're not going to get like a true R squared that is easily like partitioned into like the explained and unexplained variance the way that we did in the in the other models, right? So we can't do that decomposition, right? And actually Wooldridge says, basically the R squared measure from an instrumental variables model will never beat any that are calculated from OLS. So they're not going to be as big. All right, so I'm going to stop there. We'll take a break till like 10-minute break, and then we'll come back and we're going to talk about some more identification rules for non-recursive models. And I fear that we may not get to our nesting equivalence testing until next week, which is sad, but I promise we will do it next week. We'll see how it goes. Oh, good, that's good. And you made it here for the last part. That's good.
I'm so sorry. It's okay. I was like,
I have not been my goal for this afternoon. I got one Monday night. You just what? Just started it. But I wanted to. Oh wow, that was a long. Yeah, we extended it. Oh. Trying to get no sleep, and I am doing my best. Okay. So I'm very hormonal. Oh. It's just no sleep. Okay. I guess this is no longer applicable though, because she just told us in the beginning of class before you came in that you don't necessarily have to hand calculate it, which is what. Oh, okay. So before you came in, she said you can compute it by hand or do it in M+. Okay. It'll be equal either way. Okay. It seemed like from what she was saying, like using the standardized coefficient on the output, and then inputting and then calculating by hand would be a little bit easier. Okay. Than using M+ coding. Okay. That sentence doesn't make sense to me because I haven't done this homework yet. I'm just trying to take myself to that. I haven't even watched the whole class from last week, so I didn't either. I started it like after my full day yesterday, and I could like feel my brain just starting to hurt, and I was like, okay. And I was like, okay, you're gonna do your homework. You're gonna watch the class and do your homework all Tuesday. And I was just, my brain was like, yeah, we were. I could not. I was like, this is so inefficient. Just spending hours. So I think this is what I'm gonna do, but again, I watch the class, so this doesn't really make sense to me. Right. But feel free to use these notes. I have no idea really what they mean. So for what this is worth, who knows?
Sarah, I'm just gonna go back to that first page.
Do it. Take it off. We'll figure out. Is it letting you?
Oh, totally. Are you still exhausted? Like, did you get some sleep last night? Did Mia let you get some sleep?
I feel badly. She was like, she got a cold on the plane somehow on the way out, and it just like wrapped her.
Yeah.
The whole time, so. Yep. Okay, so this is another thing I wanted to show you. So I went to office hours yesterday, imagine doing office hours on the and
You were able, because you were
I
going to.
know I wasn't, but after, we met for advising, I was like, let me see if I can get an answer.
Yeah.
It did not make sense to me, but it feels,
Okay.
so.
I feel like this is a totally, actually, I'll still do it.
You do it, but I'm like, again, I wish I could explain what I'm meaning, I just was.
I'm getting it, I'm getting it.
I was totally scripting what you were saying.
Like right after I talked to you, they finally got the broken down tractor trailer. They got it off the road, and I was like 80 miles an hour.
Oh my gosh, that feeling is so bad. It's such a bad feeling.
It is, and I hate when I never call anyone when I'm driving.
You
But I
can
was
see,
stuck, and I was like,
I get on the road
man.
at 7 a.m. on Wednesday, so. I got you. Okay, so, I'm gonna show you. So you know that we're only doing part two.
Yes,
Okay.
thanks to you. I haven't finished the class yet.
No, okay, so then I took notes
Mm-hmm.
on just like what I was hearing. Granted, I
You
don't,
email me that?
I don't understand like what this is.
I think we'll understand after we.
I was like, math H, I don't know, I
Yeah.
haven't watched the class yet, oh
Yeah.
no. So this doesn't.
That's
make
how I
sense
do
to
it
me.
too, like I put in comments, like whatever someone says, I'm
Yep.
like screen grabbing from the chat.
Yeah. So I'll,
Yeah, just the comments, I don't want like your.
no, this is from the chat.
Oh, that was from the
Yeah,
chat,
yeah,
okay.
yeah. I'm just gonna try to put it in italics so that you know what's maybe like this, if this makes sense to you. I'm confused, everything says that, yeah, she's still working on it, like.
Yeah.
Whoa!
Yeah.
So I don't know.
So that's so exciting that like you were so inspired by Sarah's presentation. She's starting to do, she's a postdoc in the okay.
I'm like starting to think of what I'm doing, and then it just like was exciting to coalesce
Yeah.
as like, oh, I can do replication of this
Yeah.
with elementary students. And like, the fun, which I kind of really is like our SSI. And I said that, I mean, so
Like, I'm surprised she was so surprised to hear it again, because I
Yeah.
so I was just like, dude, it's so fantastic.
My worry is like, okay, I'll let
How I feel
you
about my anxiety accidentally.
Yeah, my
more motivated than class or want.
Content goes down, grades go up.
I don't remember this. Oh, you mean for that class? Yeah.
Makes me nervous.
Because of that. Yeah, oh, totally. Like, we were talking through it, and I was like, this is gonna be amazing.
Yeah.
But
My SSR.
you have lasting stellar experience.
But that's why I'm going into my kindergarten. Yeah, feel more comfortable, or do I fill that gap myself?
Yeah.
So.
But you could go to that thing in Wisconsin.
So she said it's only for doctors.
Oh.
So,
that sucks.
Yeah.
I thought, because I had saved it like in my Twitter, because I was like, this sounds interesting.
Yeah.
For the same reason,
Yeah,
so it's
yeah,
like
yeah,
SSR class.
Yeah. Okay. That's great. Scribble notes. He's choosing to.
Everybody, did anybody not get PowerPoint? I meant PowerPoint. All right. Let's go ahead and get started. So now we're going to talk about identification of non-recursive models. So we already talked about using instrumental variables to identify non-recursive models, but there's a bit more that needs to be said about identification for non-recursive models, because it can get quite messy. And this is one of those cases where things get messy fast. Okay. So here we go. Here's an apparent sufficient condition. So all models that meet the following condition appear to be identified. All right. If between any pair of constructs, X and Y, so any two variables, X and Y, if no more than one of the following is true, X causes Y, Y causes X, or X and Y have a correlated disturbance, or X and Y are correlated exogenous variables. So if only one of those things is true, then if for all, if for any pair, for every pair of variables in the model, if for each pair only one of those things is true, then it appears that the model is identified. Now, this is really interesting. This is one of those cases where, like, that seems like a relatively simple thing, but there is actually no known proof for this condition. That's why it's an apparent sufficient condition. Nobody's found a case in which it doesn't work, but nobody's actually proven that it does work in every case. So for the purposes of this class, you can bank on it, all right? I doubt that you're going to find a case where it doesn't work if nobody else has before you. But again, like, when we talk about identification rules, we're talking about conceptual identification rules. You could still always have problems with empirical under identification, which is like the data, the way, there's something about your data that makes it under identified in this particular case. So that's just a little caveat. Okay, so that's the first thing. So if only one of those things is true for each pair of variables, seems like that model's identified. I started talking about block recursive models. We can partition models into blocks. And even though the causal relations within each block are non-recursive, the effects between blocks are unidirectional. That's what's called a block recursive model. And block recursive models tend to be easier to identify than completely, like, crazily non-recursive models, as you might expect. So if you have a two equation block, so block recursive models that break into two equations within block are actually pretty common. And Rigdon has come up with like 8 identification rules of thumb, which are far more intuitive actually than the formal methods for figuring out identification for non-recursive models. But so I'll talk about Rigdon's rules first, and then I can show you some of the more formal methods to determine identification for non-recursive models. But again, like, it's just we got to think about a lot more here than we did with recursive models. Okay. So again, this isn't the full model here, I'm just sort of showing you the piece, the block that we're talking about here. If you have two endogenous variables that are linked only through their error terms, you know, you're going to end up, that's going to be a model that's identified. So basically, you know, if you had like X predicts Y1 and Y2, and then you allow for correlated residuals or correlated disturbances, that's going to be an identified model. And that's one of the reasons that even though technically when you correlate the disturbances, when I told you when you were making just identified models, I said, well, you know, you could make a path from, for example, a path from Y1 to Y2, a path from Y2 to Y1, or you could correlate the disturbances of Y1 and Y2, because if you're in a block recursive situation, you allow for correlated disturbances, that ends up being identified, and, you know, that's not problematic. So those are sort of easy to deal with. Okay, here's a case where that isn't identified. So here we've got a case where Y1 predicts Y2, and now notice there's a disturbance. The disturbances of Y1, again, so I'm just sort of zooming in on pieces of this model. So something's happening before this in the model, imagine. But like Y1 and Y2, those disturbances are correlated. And this is not like a block recursive. This is much more like sort of the IV kind of thing that we saw, right? And Y1 has no unique predictors. Y2 might or might not have unique predictors. In this case, this is not identified. So notice this isn't a reciprocal feedback loop, okay? It's just Y1 predicts Y2. There might be other variables. There could be other variables that predict Y2. There might not be. But we don't have any instrumental variables for Y1 there. And we have that correlated disturbance. So that example is not identified. And it really doesn't matter how many things might be uniquely predicting Y2, it's not going to save us. All right. Case 3. Now, and you can kind of compare and contrast case 2 and case 3. So here with case 3, we have the same thing that we had before. We've got Y1 predicts Y2. We've got a correlation between the disturbances of Y1 and Y2. But instead of having predictors of Y2, we have predictors of Y1, which that means that, right, Y1 can kind of act as an instrument here, right? We've got a unique predictor of Y1. So a block like this is identified. Yeah.
So going back to case 2, it could be identified if we were just doing the knowns and unknowns, but because of the rules we have for this, it's not identified.
Yeah, that's exactly right. So like this whole idea of counting the knowns and unknowns and just making sure we have non-negative degrees of freedom, that works for recursive models. And it works for recursive models. It actually even works for recursive models that just have like correlations between disturbances within a block, but not these are sometimes called bow-shaped correlations between disturbances. So once we get into these non-recursive models, just having positive degrees of freedom or non-negative degrees of freedom is not enough. And this is really like the hardest thing about non-recursive models. I don't think the hardest thing is the loop enhanced effects. That's, I think, kind of fun and easy. I guess finding good instrument is hard, but that's more of a conceptual hard. That's not really a modeling hard. The hardest thing about non-recursive models is figuring out if they're if they're really like messy non-recursive models, the hardest thing is figuring out if they're identified or not, right? Which is why when we did the original earlier in the class, I was like, okay, we're just going to talk about recursive models. We don't want to talk about identification for non-recursive models till later because it gets messy, right? Okay. So that's case 3. So that is identified. Case 4. Again, some of these relate to things we already talked about. We got a reciprocal feedback loop here, but there are no instrumental variables. It's not identified, right? So we already talked about this. No instrument, reciprocal feedback loop, definitely not identified. What would we need to do to make this identified? Add one IV. And if we wanted to correlate the disturbances, add one IV for each of the causal variables, right? So again, case 5, without a correlation between the disturbances, As long as we add a unique predictor for either y1 or y2, this model is identified. Okay? But if there is a correlated disturbance, right? If I only have one IV, now I'm back to it's not identified, right? And how am I going to fix that? You can kind of guess, right? Case 7 is going to say, hey, if I have an IV for each problematic causal variable, this is identified. Okay, now, and again, this is one of the things that, I mean, if you have a really big model and there's a lot going on, this is one of the things that's kind of hard to, you know, you just kind of have to parse stuff out. So case 8 is reclassify shared predictors, okay? So if you have, look at x1 there, right? x1 is not an instrumental variable because it predicts y1 and y2. So if you have a predictor like that, shared predictors, they don't actually help you identify the model. Like x1, if you think about it, just brings enough information basically to identify its own parameters, you know, but it doesn't help you to identify those unidentified parameters. So what you can do is when you see something like this, you basically like, and notice I'm saying conceptually, not in your model. I'm not talking about an M+, like on paper or in your head. When you see something like this, you drop out any of the variables that are predicting both y1 and y2, because they're not going to help you to identify. So you can just basically conceptually drop this out and then say, okay, that is it identified or not identified? So in this case, right, if you drop, I mean, the x1 is not helping you to identify. So again, you don't really have to drop it out. It's just you're sort of thinking about going back to your previous 7 cases. Would that be identified or not identified? Not identified, right? We don't have any instrumental variables and we need 2 of them in that case. So when you have shared predictors, you can just kind of drop them out in your thoughts and then say, okay, now looking at this picture again, which of these 7 cases does it seem like it fits? You can see, it's like a little tedious. Okay. So those are Rigdon's rules. Now, there are some more formal rules of identification too when Rigdon's rules don't cover the issue. And these are a little more foolproof, but more tedious still. So, this is another tricky thing. Okay, so imagine you have a non-recursive model with feedback loops. You know, it's like non-recursive and it has all possible disturbance covariances or all possible disturbance covariances within blocks of endogenous variables that are recursively related to each other. You have to satisfy 2 conditions to be identified. The first is called the order condition, and the second is called the rank condition. The order condition is necessary, but not sufficient. So if you don't satisfy the order condition, you won't be identified. But you could satisfy the order condition and still not be identified. If you satisfy the rank condition, you're guaranteed to be identified. So, but the rank condition is the most tedious of all the conditions to check, which is probably why we're going to talk about it last. Or maybe not at all, we'll see. Okay, so the order condition. All right, here's what we do. We look at the number of variables in the structural equation model, not including disturbance, that are excluded from the equation of each of the endogenous variables. So that means there's no direct effect from this, you know, from this variable to the endogenous variable. And we need to have, like, take the number of endogenous variables minus 1. Okay, so let's say if there are 3 endogenous variables, 3 minus 1 is 2. We're going to need at least that many variables to be excluded from the equation of each of the endogenous variables. Okay?
Could you say that one more time? Betsy?
Yeah, and I'll show it to you too. So the idea is, okay, we're going to look at the number of variables, the number of endogenous variables in this model, okay? And then we need the number of variables that are excluded from each of the endogenous variables, so they don't have a direct effect to the endogenous variable. We need at least like the number of endogenous variables minus one variables to not have a direct path to each of those endogenous variables. So I'll show you what I mean. I know. So okay, so how are we going to do this? So basically, first thing you're going to do is like figure out how many variables in the structural model. Again, we're not talking about disturbances. How many variables in the structural model? And again, we're not thinking about measurement models here, right? Like we're really zooming in on the structural part of the model. This is, so if you have like a latent variable model, you would just be drawing the circles and you can like forget about the whole measurement part. We're really just thinking about the structural aspect of this model, okay? So tally the number of variables in the structural model that have direct effects on each endogenous variable versus those that don't. And the number of excluded variables for each endogenous variable has to be greater than or equal to the number of endogenous variables minus one. And if you don't satisfy this condition, your model is not identified. But even if you do, you still might not be identified. So let's look at a picture here. Okay, here we go. So how many endogenous variables do we have in this model? 3, that's good, yeah. There are 3 endogenous variables in this model. So the number of endogenous variables minus 1 is 2, right? And so for each of our endogenous variables, I need at least 2 other variables that don't have direct paths to that endogenous variable, okay? For each of my endogenous variables. Yeah, and then I don't have to worry about this, right? So let's walk through and look at this, okay? So here we go. We've got y1. Let's start with, there are 3 endogenous variables, so I already said 3 minus 1 equals 2. So y1. So we've got, for y1, x2, x3, and y2. Let's go back here and look at this. y1, right? There's no direct effect from x2 or x3 or y2, actually, to y1. Okay? All right. So how about y2? For y2, and that's more than 2, right? So we're good. For y2, we've got, here's y2. We've got no direct effect from let's see, x1, right? Or x3 or y3 to y2. Sure. Y2, let me make sure I'm saying this right. Y3, x1, and x3. That's right. So y2, there's no direct effect from x1 to y2, right? And we're talking about direct effects. We're talking about like direct paths. We're not talking about indirect effects or anything, just direct pathways. So x1 does not cause x2 or y2, sorry. X2 does. X3 does not directly affect y2. And actually there's a path from y2 to y3, but y3 does not predict y2, right? So okay, fine. So we got more than 2. We're good. And then y3 here, we've got y1, x1, and x2. Let's go back. Oh wait, that was y3, right? So yeah, so no direct effect from x1 to y3, no direct effect from x2 to y3, and no direct effect from y1 to y3. So again, we have 3 sort of, 3 variables that don't have direct effects on y3. So we meet that necessary condition. But again, it's not a sufficient condition. So that doesn't necessarily mean that we're identified. It just means that we're not identified, right? Is that right? We're not identified. But we don't know if we are identified.
This was just like step 1.
Yeah, well, this is a necessary condition. So like if you flunk this, you're out. Okay? But you can pass this and still be not identified.
Okay.
So that leads us to, and I'm going to go through this relatively quickly, and I promise I won't ask you a bunch of these questions on the exam about the rank condition. It's a little tedious, but I'll show you how it's done, okay? All right, we did that. That's the order condition. Here goes. Rank condition. This is your surefire way to check identification. And this really, relates to the matrix algebra behind the whole thing. So here we go. Oh, by the way, so this is for non-recursive models with all possible disturbance correlations. The rank condition, you know, if you meet the rank condition, you're going to be identified. Okay. And the rank condition has to be satisfied for each endogenous variable. But it turns out that like you could have non-recursive models that, like, so basically for the most complicated non-recursive models, if you meet the rank condition, you're going to be identified. There could be less complicated non-recursive models for which you don't meet the rank condition and you're still identified. Again, this is where things get complicated, right? So like, you know, the messiest of non-recursive models, if they meet this condition, they're identified. But there might be less messy non-recursive models that don't meet this condition that might still be identified. Okay. This is what I'm saying here. So if there aren't correlations among all possible disturbances, so if you have no disturbance correlations or less than all possible disturbance correlations, the rank and order conditions tend to be a little too conservative. Well, so you might fail one of those conditions and still be identified, which means there might not be a sufficient condition that can be readily evaluated by hand to determine whether certain non-recursive models are actually identified. Yeah, I know. It's kind of depressing. But here we go. So here's what we're going to do. We're going to create, we're going to create what's called a system matrix. So we're going to take the endogenous variables and we're going to make those rows. So I'm actually doing this with the same picture that we had before, okay? So we have y1, y2, y3 were our endogenous variables. And then in the columns, we're going to put x1, x2, x3, y1, y2, and y3, okay? And what we're going to do is we're going to put a 1 in the column, in a column variable where there's a direct effect on the endogenous row variable. So let me go back here. And we're also going to put a 1 in the column that corresponds to that endogenous variable. So going back here, like, where's my picture? You might want to look at your picture in your handouts, by the way. That might help you. I know I want to see my picture. Okay, there we go. So I'm on slide 82 for the picture. Okay, so if you look at slide 82, there was a path from x1 to y1. So that's why we're putting a 1 there, right here. Okay. And then there was not a path from x2 to y1, so we're putting a 0 there. And there was not a path from x3 to y1, so we're putting a 0 there. There was a path from, y1 to y1. Whenever it's the variable on itself, we're always going to put a 1. So y1 to y1 is a 1, y2 to y2 is a 1, and y3 to y3 is a 1. Okay? So that's why that one is. There isn't a direct path from y2 to y1. Because again, and notice there is a path from y1 to y2, but we put it's only if it's going into that endogenous variable, not coming out of it, okay? So that's still a 0. But there is a path from y3 to y1. So that's a 1. Is everybody with me? So let's do another row. Let's look at y2. So y2. So y2, there's no direct path from x1, right? There is a direct path from x2. There is no direct path from x3, so there's a 0 there. From y1 to y2, there is a direct path. y2 is y2, so we put a 1 there. And then from y3 to y2, there's no direct path. There's a path from y2 to y3, but again, that doesn't count. Yeah? And then y3, here we go. So x1 to y3, nope, nothing. x2 to y3, nothing. X3 to y3, yes, there's a path. y1 to y3, no, right? y2 to y3, yes, there is a path. and y3 to y3, that is the variable itself, so we put a 1 there. So that's how we create the system matrix. Does that make sense? All right. All right, so good. That's step 1. We have our system matrix. Great. Okay, we're going to start with the first. We have to do this for every variable, by the way. So we're going to use the same system matrix. We're going to go through this 3 times for the 3 endogenous variables. So we start with y1. That's the first endogenous variable, okay? And the first thing you do is you're going to cross out all the entries in that row. So see how I just crossed out everything in row 1. Now, also cross out any column in the system matrix that has a 1 in this row. It's like a game, right? Sort of, well, maybe not, but maybe not as fun as some games you play. It's not Wordle, but still fun. All right, so you see there's a 1 here. So I'm going to cross out this column. I'm going to cross out this column, and I'm going to cross out this column. All right, and then I can take the rest of what I've got. So now I've just basically got a 2 rows by 3 columns, a 2 by 3 little matrix now. And I can create like a new reduced matrix. It looks like that. Okay, you don't actually have to necessarily make a nice clean one, but here it is. And then the next thing, I'm going to look at this matrix and I delete any row that is all 0. Okay, and I also delete any row that is an exact duplicate of another row or that can be reproduced by adding the other rows together. So for example, if I had, I can't, it's not a good example for this one, but like if you had a third row, like let's imagine that this isn't here because you're never going to be able to add 1 and 1. You're always going to have zeros and ones. But like if you had this, and if there were a third row that were 1, 1, you could get that by adding these together, right? That's what I mean by that. So obviously, if there were a third row that were 1, 0, or again, I crossed this out, this 1. If there were a third row that were 1, 0, 0, 1, or 1, 1, I would be crossing out that row.
The 1, 1 row.
The 1, 1 row, yeah. But I don't have any of those things. So when I look at this, I say, okay, there are no rows that are all 0. There are no rows here that are exact duplicates of another row. And there are no rows here that I can get from adding any 2 other rows together. So I'm done, okay? I can't actually reduce this any further. And the number of remaining rows is the rank of the matrix. So the rank of this matrix is 2, okay? And remember I said this was the rank condition. So to meet the rank of condition, the rank of this reduced matrix must be greater than or equal to the number of endogenous variables minus 1. Remember, we had 3 endogenous variables, so 3 minus 1 is 2. So in this example with 3 endogenous variables, the rank of the matrix, the reduced matrix, must be at least 2, and it is. But I'm not done because I have to do this for every endogenous variable. So I did this for, I started with y1, right? And I meet the rank condition for y1. Yay! Now let's see if we meet the rank condition for y2 and y3. Okay. All right. Yeah, that's what I was just saying there. Here we go. Same matrix. I mean, this is the same matrix that we started with, but now I'm going to look at this for y2. So I'm going to start by crossing off the y2 row, and then I'm going to cross off. Here, actually, let's do this. I'm going to cross off the y2 row, right? And then I'm going to cross off any columns where I have 1s in the y2 row, right? So that's going to be cross off, cross off, cross off. The y2 row, right? Yeah, so you do it, you're going to start with a different row each time. So we started with the top row because it was y1. Now we're going to do it with the middle row. This is y2. Now I can create a new reduced matrix with this row, right? And then the question is, can I get rid of any more. Can I, oops, yeah, let's go to the next one. It's a little prettier. There it is. So can I get rid of, let's see, so I've got 1, 0, 1, 0, 1, 1, right? Okay, so I don't have all zeros in the row, in either of those rows. Neither of the rows are total replicates of the other, and I can't, add two, I only have 2 rows, so I can't add 2 rows together to get a third row. So and remember, the rank is the number of rows in my reduced matrix. So what's the rank of this? 2. And I need the rank to be at least as much as the number of endogenous variables, 3 minus 1, which is 2. So I meet the rank condition here. Check! One more. You ready? Isn't this fun? Okay, I know. It's a little tedious. Okay. Okay, here we go. So that's what I said there. Here we go. Y3. You ready? So we're going to start by crossing out the bottom row now. And we're going to cross out any of the columns that have 1s, right? Okay, so there we go. And now we can look at our reduced matrix. And we've got, let's see, 1, 0, 1, 0, 0, 1, 1, 1, right?
Wait, why do we have 4 columns?
It should be just 1, 0.
Oh, sorry. Yeah, you're right. I'm getting tired. My bad. We only have 3 columns. Okay, let's try this again. 1, 0, 1. Yeah. Throwing me off there. Let me make bigger. There we go. And then we've got 0, 1, 1. Well, the numbers weren't all the way crossed. I started looking at them, right? So we've got 1, 0, 1, and 0, 1, 1. That's why it's kind of nice to rewrite as a nice little matrix. And again, I don't have a row full of zeros. They aren't replicates of each other. And I can't get to one of my rows by adding 2 other rows together. So the rank of my matrix is 2. And I need my rank to be 2. So I'm identified. Yay! So I've gone through all of this. And having done all of that, I can now definitively conclude that my non-recursive model is identified. I know it's tedious. I get it. But there you go. That's it. Again, in a block recursive model, you can actually look at the rank conditions separately for each block in the block recursive model, which actually makes it a lot easier than trying to do it for the whole non-recursive model simultaneously. And you can evaluate the rank condition for the system matrix in each block. And then if you meet it for all the blocks, then you're identified. You might think, well, like that sounds tedious because now I got to do it for multiple blocks. But trust me, if the model is big enough, it can actually be easier to do it block by block. All right, that's a block recursive model. So here's a block recursive model. So in block 1, you can see, right, we've got block 1 is y1 and y2 are the endogenous variables, and x1 and x2 are the exogenous variables. So we only have 2 endogenous variables in that block. I cross off think about 2. The number of endogenous variables in this block is 2. 2 minus 1 is 1. So I only need my rank to be 1 here, right? I cross off this row, and then I cross off everywhere I've got 1s, and I end up with a little teeny tiny matrix that is not even really a matrix. It's a 1 by 1, right? It's like little 1. That's okay. It's all right because it's got a rank of 1, and that's all that I needed, right? And then I can do the same thing here for block. So I got to do it for y2 as well. So I do it for y2. Again, I end up with a rank of 1. And so I've satisfied the rank condition for block 1, and then I can do it for block 2. Yes?
The only way this wouldn't be like a rank of 1 is if that like single cell is 0.
Mm-hmm. Yeah, that's right. So we do this again. Oh, did you have a question?
Yeah, I just wanted to verify that the way that you break out a model into blocks is just by looking at endogenous variables. Anything that feeds into them, that's a block. And then if those endogenous variables lead to other endogenous variables, then.
So yeah, so I'm probably not very good at expressing this. I feel like I know it when I see it, but I'm not very good at explaining. But in a block recursive, so we're talking about a block recursive model. So you've got non-recursiveness going on within a block, but if you look, if you look across, like forget about what's going on within the block and just look across the blocks, it's recursive. So that's what a block recursive model is. So you could have all kinds, and this is a really simple block recursive model, but you could imagine a model where you've got like crazy zaniness going on all over the place here in the middle of the model, but then you've got like over, everything over that way is just regular and recursive and or maybe it's not, maybe it's zany stuff, but the linkage, see what I mean? Like here we've got a bunch of non-recursive stuff going on. And here we've got a bunch of non-recursive stuff going on, but if you sort of look, this is recursive, right? And this is recursive. So that's what I mean by block recursive. So like,
Yeah, I was just trying to figure out like where the blocks get separated.
I mean, in my mind, that's what I'm saying. I'm not very good at maybe totally explain. This is a block, and that's a block, and that's a block. I mean, I don't know. To me, they pop out at me, but I don't know that I'm operationalizing them in a good way.
Maybe like this model, I'm just like worried about it.
Yeah.
It's not as neatly.
Well, and sometimes they're not. Usually, when they're block recursive, you can see it.
Okay.
And if you can't see it, maybe it's not block recursive. And if you can't see it and you're not sure, then you just don't break it out by blocks. Just do it for the whole model. Okay. But if you can see the blocks and break it out by blocks, it just kind of makes it a little easier. Okay, so and this is an easy one. You're right. So okay, so we said for block 1 we meet it. Now when we get to block 2, we have y3 and y4.
I'm having a hard time finding where that is. Y3 and Y4.
That's Z1 and Z2.
Oh, sorry. I called them Z1 and Z2. My bad. Yes.
Okay.
Sorry.
Okay.
Yeah.
Why wouldn't Y1 and Y2 here be considered endogenous variables as well?
They were. We just did it for their block. But now that's what I mean by in the block recursive, we can look at each block separately. So like you could just do it for the whole model, just the way we did it before. But if you have these blocks and you just want to like look at it more simply, you can just be like, okay, I'm going to tackle this block, then I'm going to tackle this block. And if you're doing it block by block, then here Y1 and Y2 are like your predictors, right? Okay, so I can, so I already did block 1. Yeah, sorry about that. So Y3 and Y4 are also known as Z1 and Z2. But again, so here I've got just 2 endogenous variables. I'm going to put all of the variables in the model here. I'm going to do the same thing. And I'm going to meet the rank condition for Y3 in block 2. And I'm going to meet the rank condition for Y4 in block 2. And or Z1, whatever, but I meet the rank condition. Okay, so reminders, when you check the identification of non-recursive models, right, you should check the rank and order conditions, or really, I mean, the rank condition is probably best of all, but you definitely want to do this if you're maxing out on correlated residuals. If you got a really messy model, it's really good to do the rank and order condition. If it's like just a garden variety non-recursive model that isn't too crazy, as I said, these can be a little overly conservative. You can also check and make sure, like if we talked about, do you have an instrument for every one of your problematic causal variables? So sometimes you don't have to go all the way down this path. You've got a feedback loop, you can see it, you've got instruments, you don't have to do the rank and order condition, right? But this is when you've got like a crazy messy model and you can't really see if you're identified or not very easily, and you want a surefire way to tell if you're identified. That's when you're going to do this. All right. Last slide on this. How am I doing? Oh gosh, 15 minutes for the other thing. Well, we'll see. Okay, we're not going to make it. So just a last thought. So there are different ways to estimate non-recursive models. In class, we've been using maximum likelihood estimation for SEM. We are not going to use OLS, obviously, for non-recursive models. You can't use OLS. But in econometrics and economics, they often use what's called two-stage least squares or three-stage least squares estimation. You know, the advantage of using some sort of a 2 or 3 stage least squares estimate is that, you know, if there is model misspecification, you can, you know, in maximum likelihood, misspecification can sort of spread throughout the entire model. 2-stage least squares can kind of contain, you know, misspecification or bias a little bit better within pieces of the model. So that's kind of one of the reasons economists tend to like it. I don't know. I mean, we're going to stick with maximum likelihood in here. But just be aware that there are other estimation strategies that are used for instrumental variable estimation. Okay. I don't want to save any of that. So now let's go back to nesting and equivalence. Let's see here. 12. There we go. So these are slides from last week. And I got to remember where we were. We talked a lot about equivalence, right? I don't think we finished. Let's see. I think we talked about, did we talk about the measurement models?
I did my notes on, I think, slide 45.
Okay.
But that looks like it's halfway through the first burgers to first.
Yeah. I think we we'd actually talked about this. I don't think, we didn't talk about this. I want to talk about this for a minute. We're not really going to get to talk about CFA, higher order CFA models in here probably, which is really sad. Hold on. Slideshow. Current slide. There we go. But I do want to point something out that I think is important. So, you know, often people will fit higher order confirmatory factor analysis models. You know, so here, you know, this thing about this, you've got 3 correlated factors or you've got a higher order factor. So let's imagine it's like, I don't know, math self-concept, reading self-concept, and school self-concept or something, right? And in the first model over there, we're just saying there are 3 factors, and those 3 factors are correlated with each other, right? But in the second model, we're saying like, oh, there's some sort of higher order factor, and it's like academic self-concept, let's say, and it predicts, you know, math self-concept, reading self-concept, and school self-concept, right? Whereas here we just got math, reading, and school correlated with each other. Now, those models are equivalent. Why?
Because saying that all of those things are correlated is really similar to saying, hey, they probably share something in common, which could be this, like,
It's 3 paths either way.
Yeah, exactly. Like if you think about it, if you think about this as being like the think about this as being sort of like the structural part, right? Here, we've got 3 correlations. How many, again, there are 3 latent variables. So how many correlations, like, or, you know, if you sort of think about the latent variables and you do like the, you know, if you do our sort of quickie rule of thumb, which actually it's useful to think about this. B times B minus 1 divided by 2 is going to be the maximum number of correlations, or which is 3, right? And so we've got 3 correlations. And think about it, like we've got 3 factors. So if you've got 3 factors, it looks like this: math, reading, school, math, reading, school. And there are 3 potential correlations, right? And here I'm fitting 3 correlations. So this part of the model is just identified, right? And when I come over here, I have 3 paths. Let's assume that I'm gonna, you know, fix the latent variable variance to 1. So I've got 3 paths. And I can use those 3 paths to reproduce the 3 correlations, right? So, I mean, these are, yeah, you're gonna get different numbers, because here, these are paths, but I can take these paths to come up with the correlations, right? But these models are equivalent models. So, but this is really important because this is like a pet peeve of mine, because I cannot tell you how many times I see in the literature people fitting higher order models. They fit the higher order model like this, and then they're like, hey, my higher order model fits. Yay, I have some sort of a higher order construct. But the reality is, this doesn't give you a test of whether you have a higher order construct, because it's going to fit exactly the same as if you just let all of your factors correlate with each other. If you really want to test whether you have a higher order construct, how many factors do you need? You really want to test if you have a higher order construct, so you want an over-identified model in this part, how many factors would you need minimally? Well, with two, you would have to constrain the paths to be equal, right? So 2, you have to constrain the paths to be equal. I would argue that's even dumber, but I mean, but like, they really should just, I mean, think about it, like, right? You should you don't have this, right? So you should just correlate these. That is actually the same, again, mathematically, like, that is the same as forcing these to be equal to each other. Again, we'll make this be 1. But if you think about it, I had a correlation, right? Let's say the correlation was 0.49. I'm just going to say the correlation between these is 0.49. Instead of fitting the correlation, I force these two loadings to be equal, and I fit a higher order factor model. What's the loading going to be? 0.7, right? The loadings are going to be constrained to be equal, and they're 0.7. And so yeah, it looks fancier, but it's really just the same thing as fitting a correlation between these two factors. Do you see what I'm saying? And again, I've seen that too. 2 factors, paths constrained to be equal, and the person's like, yeah, I got a higher order factor model. No, you got 2 correlated factors. Any 2 correlated factors, you can fit a higher order factor model, and you can get, some, again, you can get some number, but basically you're just taking these numbers are just going to be the square root of the correlation, right? Because whatever the correlation is, take the square root of the correlation times the square root of the correlation, which is what you're doing, and you're going to get the correlation down here. So a higher order factor model with 2 factors is basically just a re-expression of a factor model with 2 correlated factors that looks fancy but is really nothing to write home about. With 3, it's just identified, so we have the same thing. These 3 paths can be used to exactly reproduce the 3 correlations, right? So how many factors do we need if we really want to test a higher order factor model? What do you think? Nobody? Not 2, not 3, 4, yes, 4, right? As soon as I have 4, think about that. If I've got 4, right, here, well, let's think. How many correlations do I have here? 4 times 3 divided by 2. So I've got 6 correlations that I'm trying to re-express with 4 paths, right? So now this is a more constrained model, right? I have picked up 2 degrees of freedom in the structural part of the model by fitting the higher order model, because I'm basically trying to see if I can reproduce these 6 correlations with 4 paths. But to do a higher order factor model and not have it just be kind of a, sort of a duh-he, right? Just an equivalent to the correlated factor model, you have to have at least 4 factors. Does that make sense? Okay, so the point here is that those 2 models that I've drawn there are actually equivalent models. Again, and this is not all of the equivalent models, but just take a look here. here are 4 equivalent models. They look really, really, really different, right? But these 4 models are going to give you, they're going to have the same degrees of freedom. They're going to have the same chi-square. They're going to have the same model fit. Do they tell the same story? No, definitely not. But they are equivalent models. And this is this is one of the sort of banes of our existence in structural equation modeling is like, I got this great model. It fits. I love it. But there are all these other models out there that are equivalent to my model that fit equally well. And I can't, there's nothing I can do. It's not like, we've been building these more constrained models, testing nested models, but like, I mean, there's a whole slew of equivalent models that fit equally well. There's nothing I can really do to prove that my model is better than the other model that fits equally well, that has the same chi-square and same degrees of freedom, other than on theoretical grounds, right? And this is where like collecting data over time versus cross-sectionally, or being thoughtful about the design of your study can certainly help in that regard. So that might help you to be able to knock out potentially equivalent models. But if you've just collected a slew of cross-sectional data, that you're not necessarily going to be able to knock out these equivalent models so easily. Okay, so here's one last example. How many equivalent models are there for this picture? And it turns out that the lower bound estimate for the number of equivalent models is 33,925. There may be more, but there are at least that many. So you can see why equivalent models are a problem, right? And you're never gonna, in some sense, you're never gonna completely solve that problem. Just one thing to remember though is, I mentioned this last time, but it's worth mentioning again. The more parameterized the model is, the more equivalent models there are, right? The fewer parameters, the more parsimonious your model is, the fewer equivalent models there are. If you think about that, that kind of makes sense, right? So, so for just identified structural models, there are like scads and scads of equivalent models, and structural models that are almost, are nearly just identified. There's still lots and lots of equivalent models. But if you have a pretty parsimonious model, I often like to say that we often focus on where the paths or the correlations are, but in some sense, the real story is where they aren't. Because everywhere there isn't a path or a correlation, we're actually constraining that to be zero. Like we're making constraints there, and that those are sort of the things that we're testing, right? So, so that's just something to think about. Like the sort of the more parameterized the model, the more equivalent models there are. Okay. So what can you do? Acknowledge the presence of equivalent models, right? I mean, that's always going to be a limitation in your limitation section. Like this model fit really well. That isn't to say there aren't other equivalent models that could have been tested that would have fit equally well. Yeah, I mean, but this one fits and I like it. So use designs that limit the number of plausible equivalents. So, again, going with like a longitudinal designs can really be helpful in that regard. Obviously, experimental designs. There are things you can do from a design perspective. We're going to acknowledge those problems. If there's a way to revise the model so there are fewer equivalent models, that can be a good thing. This is what Hirschberger says, right? So acknowledge the severity, acknowledge the limitations, revise the model to decrease the number of equivalent models, find a design that's not plagued by the problem of equivalent models. Or number 4, cancel the study. Probably not what you want to do, right? But so Hirschberger's written quite a bit on equivalent models. These are 2, then there are lots of things that have been written, but I think these are 2 of the more readable things. So Hirschberger wrote a chapter in Hancock and Mueller's SEM, a second course. Larry Williams has a chapter in the Handbook of SEM, which this Handbook of SEM is really actually quite, I'm not usually that fond of handbooks, but that's actually quite a nice handbook. It's got a lot of good chapters. Okay. So let's talk for 2 minutes, but I'm not going to get to the example. I'll show you the example next time. That means, by the way, that you do not have to do that same thing that was on last homework is now on this homework. You still don't have to do it. Here's what I'll do. At the beginning of class next time, maybe I won't show you Bentler's thing because it's 12:14. I'll just tell you what I'm going to do and then it'll be done. At the beginning of that class next time, we will pick up with the Bentler and Satora method for testing for nested and equivalent models. So sort of this net testing it's called. I'll show you how to do that. You will have the option of doing that piece of homework that has now been twice on your assignments as an extra credit. So I'll make that a total extra credit assignment. I don't know how many points it'll be worth, maybe not a full 6, but probably 4 or 5 points. Got to go back and figure that out. But I'll make that an extra credit. So if you're worried about your homework grade, that'll be a great way to bring up your homework grade. We'll make it due by the day of the exam. And I don't think there's really anything on the exam that deals directly with nested and equivalent models like this part of it, like how you actually do it in M+, because as I said, the exam is really not about doing stuff in M+. So how does that sound for a plan? So next week, we'll start with the Bentler. I'll show you how to do the nested and equivalent model stuff. We have a couple more slides, but mostly it'll be showing you how to do it in M+. Then from there, we will move into review. So I'll give some overarching thoughts about like what the exam's going to be like, things you should definitely make sure to be reviewing, how you should prepare, that kind of thing. But what I think is really helpful is if you come prepared with questions. So I'll have a little like spiel that I'll kind of do that's just overview and overarching stuff. But this is a great time for you to ask questions about things that still confuse you. And again, with a real focus, not on minutia from M+ script or homeworks, which again, if you have questions about that, feel free to ask me, but none of that's going to be on the exam. So maybe you're better served talking to me about that outside of class, but really thinking more about the concepts, right? So like nesting and equivalence and, identification and, counting degrees of freedom and, what is it, how do you know, right? Et cetera, like the sort of one of the fundamental things that we've talked about in this class. As I said, I'll start out by telling you what I think some of the fundamental things are, but go through your notes between now and this week and think about what are some things that you still feel a little like, I'm not sure if I understand how this and this fit together, or I'm still a little shaky on the tracing rule, right? Still a little shaky on and just come in with questions, and they don't, they can be pretty broad. Like, can you tell us again how the tracing rule works, right? Do that one more time, whatever. It doesn't have to be super, it could be very specific or it could be more general, but I will take my sort of lead from you all, and I will just answer all your questions, and then we'll call it a day. And if you don't have any questions, we'll get out of here really early, but that's not necessarily in your best interest. Yes?
So on the homework machine, which I just opened, we can do numbers 1 through 10, and then we can do the extra credit from what we've learned today, but we're still ignoring the part 2. Is that correct?
Yeah. Oh, yeah. The extra credit for part 1 you can still do because that's about non-recursive models, but you're going to ignore part 2 because that's doing this net testing that I haven't shown you how to do. And that's the piece that I will take out and put in a separate extra credit assignment that you can then do next week.
Okay.
Yeah? There is no homework 14. There is no homework 14. 13 is the only one. So like after this one, you're done unless you want to do the extra credit. And I could say like, well, you're just done, but I know people were clamoring for extra credit. So I think it's nice to just say, after I show you this next week, you can do it you can not do it, or you can do it for extra credit if you want. We'll just make it due by the final.
Okay.
Does that make sense? But that's the only thing you'll have to do for homework other than study for the exam, which you don't really have to study for. Just get organized for the exam. Understand. You don't have to memorize anything. Just understand everything and you'll be fine. No pressure. No pressure. Yeah. Yeah, that's right. Oh, I thought I said 3.5, but if you want 4, you can have 4. What? I really don't either. I think I said 9 to 12:30 for the exam. On Wednesday, and it'll be in here. So I'll start people as early as 9 if you want to come at 9, and we'll stay as late as 12:30. It's like, I really think most people will be done in 2 hours or less. Some people will finish in an hour. I mean, I think an hour is about the fastest you could finish. Most people will finish somewhere between like an hour and a half and 2 hours. And some people will take the entire time. But in my experience, those people spend the last hour and a half on like 1 or 2 questions where they're like, oh, I'm not sure if I circled the right thing, right? And so I have to save them from themselves after 3.5 hours and rip the paper out of their hands. Because it's not like you're writing essays and you're not done. Like, there's no way you won't be able to get through the whole exam in an hour and a half, you know? But
Could you indulge us and bring like an example, multiple choice an example?
yeah, I'll bring a couple of examples to give you sort of a flavor for it. Absolutely.
Okay, that'd be helpful. Because the flavor of like homework problems.
Yeah, it's very different. So I'll bring a couple of examples.
Thank you.
Sure. All right, well, we're done.
Thank you, Betsy.
You're welcome. See you next week. Okay, stop sharing. Stop recording.